Hello. Good morning, all. Am I audible?
Yes, sir, you are.
Okay. So good morning, everyone. I welcome you all to this Join FDP in Python programming. Today it's day 7. So today's session will be taken by Ashwini Kumar sir. He has done his master's from University of Miami, Florida, with 100% scholarship. He also served there as an educator. After completion of his master's, he was employed by Lucent Technologies, formerly Bell Labs, as software developer. Over the last 20 plus years, he has worked as a software developer and educator in various MNCs. So I would like Ashwini sir to formally start today's session and kindly start with the day 7 session, sir.
Thank you, sir. Good morning, everybody. So my name is Ashwani Kumar, and you guys can call me Ash. It's simple. Okay, so today's session is going to be about Python and how do we use Python in our engineering application. So let me just start with sharing my screen. Right. Okay. All right. Is my screen visible to everybody? Okay, can I get some confirmation? Okay, thank you. Yes, thank you. All right, thank you. Okay, so let's start with a simple application. I'm sure most of you at some point must have dealt with different units of temperature. So you have Fahrenheit, Celsius, so on and so forth. So let's deal with something simple. Let's say you want to design a simple function. Let me move this over here so it's not in the way. Let's say you want to design a simple function, and your function is going to convert Fahrenheit to Celsius, or maybe Celsius to Fahrenheit. So you want to write your Python program. So when you write your Python program, you need some type of IDE. IDE is basically, think of that as a place, as a text or a code editor where you can write your code. So there are a lot of tools available. Jupyter is one of the most commonly one. This is the one that I use very often. It's a great Python IDE tool. Is great for educational purposes and also to experiment with your code. There's another one. It's online. This one actually you have to download on your machine, on your computer. This is the one that I'm using. I actually downloaded from the internet. Then there is one on the web. There are a lot of online Jupyter online editors available on the web for free. And so one of the main ones is a Google Colab. So some of you who actually have done Python programming must have heard about Google Colab. So this is the one. You can actually go create an account over there. It's free. Just type Colab over here or just type Google Colab. And this is going to take you over here. So from here, you can actually log in using your Google account and it's free. They don't charge you any money over here. But it comes with a condition that you can only use this Google Colab. If you are using a GPU, you can only use GPU for a certain amount of time. But for the most part, I think it's like 8 or 10 hours in a month or something like that. For the GPU, you're okay. CPU, you can use as much as you want. I think that's okay. All right. So I'll be using for this educational purpose my Jupyter notebook that's installed on my local machine. So let's start with a simple code. Let's print something. Print hello. I'm sure you know how to do this, but I'm just going to give you a short tutorial real quick. So you type print hello, and this is a run button right here. Just click on run button, and there you go, it prints hello. All right, great. Now let's say you want to design a function that converts your Fahrenheit to Celsius. So the way you do, you define a function, and you say def. Anytime you define a function, you use def. And let's say it's a good idea to actually call your function a descriptive name. So what I'm going to do, I'm just going to do copy and paste and explain the code because our type, it may take a little bit too much time. So what I'm doing right now, I'm defining a function. I'm calling my function F to C. All right, Fahrenheit to Celsius. Excuse me. All right. I joined already. Okay, so you define this function f to c, and basically what it does, it takes this parameter. Fahrenheit is my parameter. It's an argument, or another word for that is parameter that is supplied by the user, and it takes that number, whatever the number is given inside, and it's going to apply this formula. If you recall from your high school, this is a formula that's actually used to convert your Fahrenheit temperature into Celsius. Celsius is equal to Fahrenheit minus 32 times 5/9. And then it returns the Celsius. That's all it does. Okay, so let's say I call this function and I say C equal to F to C. And let's say I want to convert. Yes, sir. Does somebody have a question? I think I can hear something in the background. Okay. All right. So you say F to C, and let's say you pump in some numbers, 100, and now you want to print this result out. Type print C, and let's run this. 37.777, so on and so forth. So it prints your result. It converts this 100 into Fahrenheit. Great. So just to give you a little rundown, what's happening over here is that this 100, this particular line, it calls this particular method. So the 100 gets substituted inside Fahrenheit, and now it becomes 100 minus 32 times 5/9. Whatever the answer is, 37.7. The Celsius becomes 37.7. Then it returns the value. When it returns, your C becomes 37.7, and then it prints out the value. All right, great. Simple, nothing fancy over here. Now, what if you want to go the other way around? You want to convert Celsius into Fahrenheit. So come over here. Let me remove this. Actually, let me just create another one. So these are called cells, by the way. These things in Jupyter, they are called cells. So you're executing each cell one at a time, just to see if it's working or not. So now I'm converting my Celsius to Fahrenheit. This is the logic I'm using. Then I just call my print, same thing all over again. Just type this particular method, Control C. This time I'm going to call it C to F. C to F. And let's print out my value. And there you go, 212. Okay, this is simple because all you're doing basically taking one number and converting Fahrenheit to Celsius, Celsius to Fahrenheit. Okay, what if you have a series of values? In real world, you're not going to work with one value because you can do with your hand something like this. So what if you have a series of values? And this is where you actually can use these libraries. So let's say you have a series of values. So let me just remove this. So let's say you have a list of values, 98.6, 20. Excuse me, let me just leave some space in between so a little bit legible. All right. So let's say you have a list of numbers. Your numbers are 98.6, 20, 30 Fahrenheit. These are your Fahrenheit data. This could be basically, I'm just making three numbers, but this could be in reality, could be 100, 200, 1,000, 1 million, like whatever data it is. So this could be a huge data. You convert this into your NP array. Now, the reason you want to use your NumPy is because NumPy is a very good library, and what it does, it actually is very good at handling your matrix multiplication. Anytime when you have to do this computation like multiplying numbers, multiplying matrices, or doing this doing this heavy computation, your NumPy is your go-to library in Python. So I'm converting my list into NumPy array. And one thing about this NumPy is that it gives you these additional built-in functions. So that function can allow you, it basically allows you to perform multiple computation on these values really fast. Okay, so I import my NumPy and I'm creating an alias. I'm calling it that, hey, import my NumPy and give it a name as an NP. I don't have to do this, but that's something I like to do because this way I don't have to keep typing NumPy every single time. I want to use the word NP now. So I'm just creating an alias for that. So then I get my list, square bracket means list, and I convert my list values into a NumPy array. So the way you convert is you say np.array. np is my numpy, which is right here, dot array. So it's gonna call the method array, and it's gonna convert all these numbers into a list. I mean, into an array. All right, great. Then I call my function f to c, which is this function right here. So let me just copy and paste this function. Okay, I just somebody raised their hand. Let me see. How do I get this thing working? Yes, ma'am. Somebody raised their hand.
Yeah,
Go ahead.
sir, I had a question. We are converting list into array
Yes.
before passing the values to F to C. Why do we need to convert it? Like, can't we directly pass list to the
Okay.
function?
Great question. Thank you. So, yeah. So, could you unmute yourself, please? I'm sorry, mute yourself. So this way, otherwise, there's an echo gonna be happening in the room. So yeah,
Uh,
yeah. So Dr. Namita, yeah. Thank you for asking this question. So yeah, what happens is your NumPy is a library that actually does a very fast computation. So list, when you're doing some like, let's say, computation on a list, it can take some time. Number one. Number two, your NumPy library is designed specifically for heavy computation purposes. So certain things you can do in NumPy a lot faster. For example, you get these functions. Let me see if I can show you if it's over here. Let's say you want to round everything. Okay, let's say you want to calculate a mean value of all these values. So let's say you have a data and you want to calculate a mean value. Well, one way to calculate mean is you would have to design a for loop and loop through the whole thing, add them all together, and then divide by the total number of elements, and that's going to give you mean. Your NumPy has these inbuilt functions that calculates the mean for you a lot faster. So when you're working with the data that has maybe hundreds of thousands of records, and you are working under time constraint where you are
sir, you
NumPy,
aren't
because it's
audible.
very fast. It's very fast. Okay. In short, it's very fast. Okay.
Thank you, sir.
So I convert. You're welcome. So I take my list, convert it into NumPy array. And then I invoke my function f to c, which is right here, this function. So I invoke my function, and then I print. So this is the way I print, by the way. So let me just. Okay, did somebody ask me a question?
One question, sir. So when
Yes,
we
sir.
are using NumPy, in the list we have to use only number, or we can use any other, that means some character also.
Yes, you can use characters too.
In that
And
case, when you
generally,
convert,
yes, sir. Go ahead.
one more thing, sir. If I use character in the list, and in the array means all the characters are same type. If I take in a list with number and character, then we convert using NumPy array, then is there any problem?
Depending on what you're trying to do. If you're trying to multiply, let's say you have a list and your list contains string and you're trying to multiply that by 3, that's going to be a problem. You cannot multiply a name. Let's say your name is Subhash. You cannot multiply Subhash by 3. It doesn't make sense. So in that case, yes, it's going to be a problem. Okay, so yeah,
Oh.
what I would do, gentlemen, is I would actually play around. Like, let's say you ask me this question. Great question. Let me move this over here. And let me, yeah. So let's just come over here. Let me just create a list real quick. And let me create a text something. Let's say abracadabra, abracadabra. All right. Create my list and let's run this cell and let's see if it runs. All right, successful. Now you multiply this thing by some numbers. So let's say temp underscore f. Actually, let's say plus 3. Okay. So r equal to temp plus 3. Basically, I'm adding 3 to all of them. Now, this should give me a problem. Would it give me a problem, or yes or no? The answer is the people who created NumPy this is something called operator overloading. So people who created this NumPy library, have they taken into account that if somebody enters a string, then what to do with that? If they have taken this into account, then maybe it's going to work fine. But if they have not, then this should throw me an error. So let me remove this first, okay? Let me just do it without that. And let me print out my R. All right. So 101.6, 23, 33. You see, I added 3 to each one of them. Now I add something, a string over here. And let's say the string is Yahoo. All right. Let's see what it does now. Oh, look at that. It gave me an error right there. So the creators of this NumPy library, they have made sure that when you're adding a number to that everything inside of this has to be a numerical data. All right, and that's why you get this this message. ufunc add did not contain a loop with signature matching type. So it's telling me that these are the types it should have: u32, int32, and so on and so forth. It does not have that. That's why it gave me the error. But
So
I wonder. So yes, sir. Go ahead.
so is there any way to like to restrict the data, like it should be homogeneous or heterogeneous? Because
Yes,
being a
you can.
human being,
Yes, you can. You can actually put these exception clause. These are called error checking, and you can actually put an if condition somewhere over here. So anytime when you get your data, a lot of time it may happen that your data would be wrong, and this is where your data cleaning comes. You have to clean up your data. So you as a programmer would have to ensure of that. You would have to actually do some coding and make sure that the data comes into the list is the right formatted value. Okay. Moving on. Right here, let me just. All right. So now I have. Oh, let me see where are they. Okay. So now let's say I have this list of numbers. Okay, and I convert into NumPy, and then I call my temperature F2C. It's gonna
so
take this
my
Fahrenheit.
my question was like so NumPy does not facilitate any function which will be refining the data, or like we need to do manually.
When you say refining the data, could you be a little bit more clear? What do you mean by refining?
Meaning homogeneous or heterogeneous, similar type of data.
It does actually. There is a function called int as type. If my memory serves me right, there is something called as type. So you would have to
Okay.
use, let's say this, yeah, there is something called as type. And this way you can convert everything into int or float or object. There's another one called object. So yes,
Okay.
there is. So you can do that.
Okay, thank you.
If that's what you're asking me, yes.
Yeah, I was asking some similar thing. Thank you.
Okay, now I convert everything into my list. I mean, sorry, into my NumPy. Done. Now, then call my function, which is my F2C right here. F2C is going to convert Fahrenheit to Celsius. What this function is going to do, one of the coolest thing, is that it's going to take this whole elements, each one of them, and it's going to apply to each and every single element, and it's going to print out my answer. So let me just comment this line out, and let me just type over here, print temp C. Okay, I'm printing my temperature C. And if I run this, and there you go, look at that. 37 minus 60 minus 6.66 and minus 1.11. All right, so it just did these three values. Great. You see that in one, I didn't have to create any for loop. Okay, if you're working with, let's say, list, if you would have worked with list directly, you would have to design some type of for loop in order to execute something like this. Now, if I use list directly, okay, let's say I used list directly. Let me just copy and paste it up there. You're going to see, oops, sorry. Forgetting where my control V is. All right. Oops. Right there. Let me say if I remove this completely. Okay. And if I list F and I'm calling F2C in list tab. And let's see what happens. Oh, look at that. It gave me an error. Okay. And the reason it gave me error is because this function, this particular function, it is not accepting, it only accepts this, where it is. It's accepting a number, Fahrenheit. Okay. That's the problem. But when I pass it a NumPy array, your NumPy array, it happily executes that because it treats the NumPy array as a different type of element. Okay, it treats it a little differently. So when I'm now calling it, converting into array like this, and then when I run this, it works just fine without any problem. All right. So now I have converted this whole list right here, these 3 elements into from Fahrenheit into Celsius. I can hear something in the background. It seems like somebody mic is on. Could you mute yourself, please, sir? Thank you. Okay. So it has converted everything into temp, into the Celsius. Now I don't want it to be written like this. Maybe I want a little bit more descriptive name. Maybe I want it to return so that this way it makes a little bit more sense. So let's do that way. So I use something called F. F is basically formatting. Okay. So I'm saying F, double quote, and then I say Fahrenheit. Let me actually, do you guys know about Fahrenheit? I mean, this F format part. Let me give you a little short tutorial real quick on this. Okay, Fahrenheit is this thing. All right, Fahrenheit to Celsius. So let's say I print this statement. Run this code, it prints Fahrenheit to Celsius right here. Okay, I want to print my variable in there. So the way I print my variable is I use this curly braces. Okay, and when you use the curly braces, you have to make sure that you're using this F in front of it. F is a short for format string. So I'm using my format string. And over here, you can specify your variable. So your temp C is your variable. Put it inside this curly braces. And now when I run this, it's gonna print Fahrenheit to Celsius is, and it's gonna print the value of this variable over here. And if I run this, and you can see Fahrenheit to Celsius is, this is the value of that variable right here. But this is called formatting string. Okay, this is the way you format. So this is the one that I use. A lot of people sometimes they use comma. I don't like the comma one. I'm more comfortable with this, and it's a little bit more intuitive for me. So that's why I favor this one. So going forward, I'll be using this convention. Okay. So I converted Fahrenheit to
sir, like in this print F Fahrenheit to Celsius is temp C. So whatever is in double column, so that will be printed as it is, na?
What is in double colon?
Like print F double colon Fahrenheit to Celsius is temp C, and this whole goes in double column. Okay. So so how will it execute temp C because it is in double column?
Double column. I don't understand. Double column. What is a double column?
Double quotes. It's double quotes, not double column. It's double quotes.
Yes, double
quotes.
How will it execute temp C then?
Okay, so you're not gonna put in double quotes, and the reason you're not gonna put double quotes is because you see this quote right there. This is gonna conflict with this quote. So you can use something called backslash over here, but for the most part, let's see, you can actually put single quote. You can put single quote. All right. So this way, it's not gonna conflict with this double quote. Okay, you see this double quote right there. You don't want it to get conflict. So basically, I'm using single quote now. And let's run this. And there you go. You see it printed single quote right there. All right. Okay. I hope I'm able to answer your question. All right. Yes. Now, I printed this thing out. Now look at my numbers. They look weird. You see that 37 point, and then there's nothing over there. Minus 6.6666, minus 1.1111. That is a weird looking number. I don't like that. I don't want my numbers to be rounded off. We all like rounded numbers. We come from technical background, and round numbers makes us happy, or at least it does to me. So how do you round something? Well, you can round something. NumPy gives you the ability to round a number. Very easy. You just call np dot round, and then you specify your variable. So my variable is temp underscore C, and how many digits I want to round off? 2. So what I'm doing in this line is I'm taking my temp C variable, which is right here, the whole NumPy array, and I'm saying that round it off to the 2 digits. And then I'm saying equal to. So I'm just overwriting my temp C. Okay, now I'm going to print my temp C out, and you're going to see everything rounded nice and neat. And there you go. I'm happy now. All right. So let me comment this line out. The way you comment a line out, you put an octothorpe in front of it. All right. Now I'm going to say, I'm going to make my message a little bit more descriptive. I'm going to say F Fahrenheit temp F, which is right here. 2 Celsius is my NP round. Let me remove this part now. And let me put temp C over here now. Is temp C. And let's run this. And look at that. Fahrenheit, this, to Celsius is this. So it has converted this temperature into this temperature. Okay. So this is how you can actually use NumPy array to convert from one type to the next type. Next topic. Now let's say, so this was a series of values, right? We converted a series of values. Simple. And this one now you know how to convert series of values. Let's look at another example. Let's say you want to calculate stress. Now you know the formula for stress is force divided by area. So I create a function called, let me just copy this and paste it over here. Oops. All right. So I do define my function called stress. The stress is, it's going to take 2 arguments, force and area, and it's going to return force divided by area. That's what it's going to do. It's going to return force divided by area. So I define my force. Force in Newton is 5,000, and area in meters square is 0.005. So this is my force and this is my area. And I want to calculate my stress. Only 1 digit, by the way. This is only 1 number, okay? So in this case, when you calculate your stress, you call your function called stress right here. It's going to call this function, and it's going to pass this argument, which is my 5,000 and 0.05. It passes this as an argument, and when it passes that, my function comes over here. So 5,000 0.005. So 5,000 divided by 0.005, and whatever your answer is, it returns it. Okay, so when it returns it, that return value is captured by stress PA. So this one captures that value. So once I have captured that value, remember, this variable can only capture it if you have this equal to sign, and if this function right here, this function is returning something. If it is not returning something, it is not going to capture. If I just type something over here, let's say print something, this is not going to work. But in this case, it's returning something. That's why it's able to capture that. Okay, and then I want to print that value out. So there you go. So stress, let's calculate this. And the answer is 1000.0 pascals. Now, there are a lot of fancy things you can do over here. You can actually put this a colon, 0.2f. So this is a nifty trick. What basically you're telling, when you're giving instructions, you're saying that, hey, this, let me actually copy and paste this line below. So you can see the difference between before and after, okay? All right. Now what I'm doing, I'm saying that, hey, you have, you have this stress PA, and I want you to only print 2 numbers after the decimal. That's what your 0.2f means. Print only 2 numbers after decimal. And if I run this, and there you go. So it's going to print 2 numbers after decimal. You see, 0.00. So this is what it means. All right. Now let's say there's no way you can remember all this. So there's no way you can remember all these commands. Oh, is somebody asking me a question? Okay. Nobody?
So what is the
right.
significance of this if letter under print function?
The
significance of
okay.
if under print function.
Oh, the F.
Yes, sir.
The
Yes.
significance. Okay, F is basically a format. It's a convention. It's basically a program. Hey,
Not
could somebody please?
the initial. So when you are starting with inverted comma, double inverted comma, that initial if.
This F. This one. Okay.
This one, sir. Yes, sir.
Okay. So this F is basically an instruction. It's an instruction given to print statement that everything that is going to be inside this double quote, okay, if you come across like a character like this, this curly braces, treat that as a variable. So f is nothing but basically instruction. The proper word is called formatting string. But think of just think of this as a special instruction given to print command that, hey, when you see inside the string, if you see something like this, this curly braces, everything inside the curly braces, treat that as a variable. So that's what it is doing. It's going to treat that as a variable. Okay. Okay. So I run this, and it prints out my value. All right, great. Now this is only one, right? There's only one value, but reality is you're going to come across series of values. When you get your data, it's not going to be one value. It's going to be many values. I hear a lot of things in the background. Could you please mute yourself? Thank you.
Sir, one more thing, in the previous, if I at the end, if I write stress underscore PA is equal to, and I don't write that F, I'll use double quote and I'll put stress is equal to double quote close, then I'll call that function stress underscore PA. So will it give me the result?
Okay, which one? This line?
Yes, last line.
Okay.
Last
Are you talking about this?
line.
Okay. Are you talking about
So
this one? Point.
yes, I won't put that what you had put. We had called that function. Stress PA. So I'll put it outside. I'll put that outside the double quote.
Okay. Okay. So you're saying put a quote over there? Is that what you're saying? Like this? Okay.
I hope he is asking if I want to print something without using double quote, then how we proceed?
You cannot.
Yes,
You
yes.
need. Yeah. You need. Yeah. You need. If you're using F, oh, without double quote, you can just say print. That's it. That's all you have to do. Print, and just say stress PA. There you go. That's it. And it prints out the number. Prints out your variable right there. Okay. So there are different ways of printing these things. I can say print stress PA is going to print like this, or if you want to use F, you can use this way. Okay. So I would appreciate like all of you, like when you ask me a question, to make sure to mute yourself after the question, because there's a lot of background noise happening, and other participants, they cannot hear you. So I'll appreciate if you can do that, please.
Hello, sir.
Okay. Now
Hello.
okay. Can you
Excuse me, sir.
Yes, sir.
Can you please share this notebook?
Okay. So I see there are more than one ways to print something like this. See, I can print like this using comma statement too. There is a print. I can use this one too. Print.
Yes, I put in chat. Just check that.
And I can say like this. Okay, this is gonna work too. So I'll just show you, like in literature. See, that's one of the good thing about Python, or maybe a bad thing about Python. There are more than one ways to do stuff. So I can say stress, okay, equal to comma, and then like this, comma, and then put this in quotes, space, comma. I can do this one too. So there are different flavors. There are different ways you can do the same statement. You can accomplish the same thing. You see there, stress
Yes, sir,
equal
this is
to,
what I meant.
and then this right here, 1000, and then Pascal. You can do this one too. Now, different people have different ways of doing it. I actually favor this one better. Okay, I like the F better because it's more intuitive. You see what you're doing, you're putting your variable stress, putting your string, and then you're substituting your variable right there. You see, your variable is in curly braces. So I like this style. And in programming community, a lot of people, they favor this. Okay. And so F is for format. Okay, format string. Oh, not string, string. It's for formatting string. So the word is format. Okay, so think of that as a special instruction. It's telling Python that, hey, inside this string, whenever you see these curly braces, inside the curly braces, whatever the value is, that treat that as a variable. Okay, now let's say if I don't put my F, let's say I forgot, I don't put F. Let me just go with here, and I don't use F now. What's going to happen now? It's going to print the whole string the way it is. So watch, this thing is going to get printed on top, and right there, you see that stress like this. It's going to print like this. But I don't want like this. I actually want the value of my stress PA substituted over there. Okay, since I want my value to be substituted over there, I use F over there then. And the moment I use F, then it prints out the statement. All right. Then I say, you know what? And then I ask myself, I say, you know what, man, I don't like this. I actually want to have 2 decimal after my digits. So I can do that one. And then I say, you know what, I don't like this. I actually want to put a single quote over here. So I can put a single quote. You see that? And then I say, you know what, I don't like this. I actually just want my stress PA printed over here. Okay, I hear a lot of things in the background. And some, could you please mute yourself? Thank you. Okay, there's still a lot of background noise. Let's see. I hear a lot of background noise. Can somebody please make sure that, you know, please mute yourself. Yeah, administration, can you please mute everybody out? Because it seems like too many people are talking. I cannot hear. Let's see, where's this sound coming from? Oh my God. Oh, there it is. Okay, Neelam Homain. Neelam Homain, please mute yourself. And let's see who else is there. Yeah, please mute yourself, everybody. And all right. Oh my God. Well, I guess we have to live with it. There's not much we can do unless somebody knows who it is. Just call them out and let them know to mute themselves out. Otherwise, you know, I hate to say this thing, but this is not going to be, you know, a pleasant experience for some of you. Because you're going to be hearing me talking and also at the same time other people talking. Okay. Now moving on to the next topic. Let's say you have. Let's say now you have series of values. Okay. In this case, we only had one value, right? Reality is you're going to get series of values, and there it is. This is my series of values. So I have series of values, right? And this is my force. My force is basically, these are my values. Okay. I'm just specifying my force. My force is 5,000, 6,000, 7,000. And my area, this area right here, these are my corresponding areas for each one of the values. For 5,000, my area is 0.005. For my 6,000, when my force is 6,000, my value is, area is 0.005. Oh, it's the same value. All right. And when my force is 7,000, my area is 0.0. So now I want to calculate stress for each one of them. So I apply my formula. I actually call this formula right here. Let me just come and paste it. Okay. All right. All right.
Dr. Subodh?
Sir,
Yes, sir. Yes, sir. Okay. So you have force N, and then you have this area. Okay. So I have my force for each one of them, and then I have a corresponding area. Then I apply my formula, SP round, and basically I just I don't need this thing. Let me remove this, and let me remove this too, and there you go.
वो जो
So
ऊपर
now,
वाली बिल्डिंग है उसके लास्ट टॉयलेट है उसमें एक ही बना हुआ है
okay. So stress PA, I apply that formula, okay, and then I print my stress, and it prints out stress is 1,000, 100,000, 120, this number, then this number right there, and in pascals. So it calculates stress for each one of them, each one of the corresponding ones. Okay, so this is a series of values. So you can have 1,000 numbers over here, you can have 1,000 numbers, and it's going to happily calculate it for you. I wrote only 3 just to show you the proof of concept, like how you can actually have many, many values. Doesn't have to be 3, it can be 4, 5, 6, 100, 200, 1,000, 1 million, just depends on you. Okay, so there is this. Now, let's do Pythagorean theorem. So I'm sure everybody in their line of work has seen Pythagorean theorem. So let's come to Pythagorean theorem. Step 1, let me just copy this. So first thing is you define your Pythagorean theorem. So you define a function, okay, and your function is this. It's going to take a and b as a value, and it's going to do square root of that. So there is a function in numpy and p. There is a function called sqrt. I'm going to use sqrt to calculate square root. Now, how do you square something? So by the way, just a short tutorial on this. Let's say you have number 2. 2 times 3. Okay, if you run this, it's going to give you 6, right? What if you want to say 2 to the power 3? So you do like this, 2 to the power 3. Okay, this is how in programming you do 2 to the power 3. And the answer is 8. And what if you want to say 2 to the power 3 plus 3 to the power 8? All right, let's run this. And the answer is 6,569. So you can do all these little, that's what's happening over here. So when you see this 2 multiplication sign back to back, it means it's raising it to the power, because on a keyboard, we don't have raise to the power option over here, right? So we can emulate then, we can simulate power by using that key. So for example, like if you look at your keyboard, okay, you're not going to find 2 to the power 3. There's no way you can write on the keyboard. So what you can do, you can say 2, 2, 3. That's what it means. Okay, so this right there means this. All right.
Giving the answer without coding. 2 to the
Now,
power 3.
So what I'm doing over here, I'm actually saying a to the power 2 plus b to the power 2. And then I'm storing that value in C, and then I'm returning my C value. Okay. So if you want to calculate, let's say hypotenuse of, let's say, I'm sure most of you guys know that if you have, let's say a triangle, a right angle triangle with side A and B as, let's say, A equal to, let's say A equal to 3, okay, and let's say your B equal to 4, okay, so you want to calculate C. So your C is going to be equal to hypotenuse, and then you substitute A and B inside, A and B, all right, and then you print out your C, print my C value out, all right, and it's going to print your C value, and there you go, 5.0. So by the way, this variable, I don't have to call it A, I can call it X. I could have called it X, I could have called this thing as Y, I could have called this thing as Z, okay, X, Y, Z, and I can just substitute over here X, comma, Y, and then print out my Z. Okay, I could use any variable. Just be aware that this variable AB is only present inside this. It is not you cannot access this variable outside, and outside variable cannot communicate with inside. The only way it can communicate with this is from here. All right, so I define my x is 3, my y is 4. I call my function hypotenuse x comma y. So my x is 3, y is 4. It comes over here. So my a becomes 3 and my b becomes 4, and then becomes a to the power 2 plus b to the power 2. It calculates that, it square roots that number, and then it returns my c. And let's print it out. It comes out with 5. So that prints out 5. It prints out my 5. Okay, so this is my simple Pythagorean theorem. All right. Now let's do the same thing for series of values. Okay, you want to calculate Pythagorean theorem for series of values. Now, oh, one more thing. Now we can do hypotenuse. Now I want to give it a little bit more descriptive name. Okay, just printing z, maybe I don't like that. I want to give it a little bit more helpful name. I want to say hypotenuse, diagonal, and then I want to say z over here. Okay, so let's print it out like that. And look at that, hypotenuse, diagonal, this. And I'm using comma notation. And I say, you know what? I don't like comma notation. And I really don't like, by the way, comma notation. I like this notation better. Everybody have this style. I like F notation. F is the format. And over here, I'm going to remove this. And over here, I'm going to use curly brace. I'm going to put Z over there. All right, let's run this. And there you go, hypotenuse, diagonal 5.0. I can use this or I can use this. I favor this better because it's a little bit more intuitive to me. Okay, so I've done that now. By the way, there are more than one ways to print. Okay, stick with the one that you feel comfortable with. And there's nothing wrong with that. All roads, they lead to the same place. Okay, now calculate the same thing for series of values. So I have my A and B and like this. Come over here. Okay, so now let's say I have a series of values. A is 3, 5, 8, 6. And my B is 4, 12, 15, 18. So that means your 3 and 4 go together. 5 and 12 go together. Let me count. Your 8 and 15 goes together. And your 6 and 8 goes together. So you want to calculate your Pythagorean theorem for series of values. So my C is going to be hypotenuse A comma B. And then side A, side B. I'm printing my side. In this case, I'm using comma. Okay, just to show you that different ways actually do the same thing. And let's run this. So my A value is this, my B, and my hypotenuse for each one of them is 5, 13, 17, 10. So what's happening over here is this. It's calculating all these values for series of triangle. So I have, oops, sorry. So I have, let's say, one triangle, right? Oh, excuse me. This is one triangle, one triangle. So one is 3 and 4. I have another triangle. Okay, which is what, 5 and 12, right? So this is 12 and this is 5. Then I have another triangle, fourth one. Which is 8 and 15. 8 and 15. And then I have fourth triangle, which is 8 and 6. 6 and 8. So what I'm doing over here, I'm calculating hypotenuse for each one of them. So for 3 and 4, my hypotenuse, if I do the calculation, by the way, I'm not doing manually, and my computer is doing it for me. Thank God, whoever created NumPy. All right, so 3 and 4, which is this one right here, is being calculated right there. And what's my answer? 5. This is my answer, 5. 5. Okay, now when I do 5 and 12, 5 and 12, these two, which is right here, what's my answer? 13. So this is 13. And if I do Pythagorean theorem applying to 8 and 15, which is right here, what is my answer? 17. 17. 17, 13, 5, and the last one is 10. This is for 6 and 8. So if this is 6, this is 8, this is 10. So see, it calculated all these values really quick for you. Now, if you do something like this in list, good luck with that. You would have to actually come up with a loop. And I mean, you can do it, but you just have to, your coding would have to be, would get involved a little bit more. Okay. Now, oh, by the way, am I audible? I just want to make sure because I'm not hearing anything that's making me a little nervous.
Yes, sir, you're audible.
Thank you. Okay, because I was so used to hearing so many sound in the background. For a second, I thought that I lost connection. All right. Okay, and likewise, you can do the same thing. Now you can calculate. Let's say you have to calculate resistance of a of a of a value, right? So let's start with here. I'm just kind of overdoing it a little bit, but I just want to give you a little bit, a little idea what's happening. So let's say you want to calculate resistance. So this is your formulas. Your V equal to 12, I equal to 2, and you can calculate resistance like this. Okay, so resistance is ohms, and then you can put your F over there, 0.2 F if you want, or don't put it. That's up to you, how you feel that day. And run this, and there you go. Resistance is 6 ohms. Okay, and likewise, you want to calculate BMI, you can do all that. All right, simple. So what's the takeaway from here today? I mean, right now, not today, but right now. The takeaway is this: you can calculate all these values using series. I mean, using NumPy, and you can convert that into a array, into NumPy array. When you convert into NumPy array, you can calculate you can solve multiple problems at the same time. So I just showed you using Pythagorean theorem that you can calculate hypotenuse for multiple right angle triangle in this one single go. So this right here, you can calculate stress for multiple values. You see that? Okay, next topic. Now, let's say, let me just close this, come over here. Now, most of the time you get your data. It's never going to be like this. Then nobody's going to give you data like this, right? I mean, reality is right there. Nobody's going to give you data like this. Your data actually comes from a CSV file. You actually go on the internet and you download a file. That's how you get your data comes. You have a sensor. Your sensor creates data for you and it stores somewhere. It stores in a file. So you should be able to read that file, and that's the real world scenario. So how do you do that? Well, thanks to the creators of pandas, we can do that. So there is a library called pandas. Okay, let me just copy this and explain you step by step. All right. So as I was saying, this is a great teaching tool, this Jupyter Notebook. And so one thing it allows you to do, you can actually write some little notes over here. So you can change this cell. So let's say I want to say now I am showing, or actually it's a read CSV file, okay? Read a CSV file. Okay, I want to turn this into a markdown cell. So over here, if you look over here, there are 3 options: code, markdown, raw. So click on markdown, and that's going to convert this cell into a markdown cell. With markdown, you can use this special syntax. So when you go like this, and when I run this cell, you see read a CSV file. It turned into a comment now. So this way you can actually write your whole code over here. Okay, write the little comments, basically what this is doing. Okay, so now I'm showing you how to read a CSV file. The first thing you do, you import your pandas. Pandas is a library. It's pretty cool library. It's used by a lot of data analysts, and one of the ability it does is that it allows you to read your CSV file. You can use other libraries too. There are many other libraries you can use to read CSV. I'm using pandas because I like pandas. I'm a panda fan. And then I'm creating an alias for this PD. And likewise, I'm importing my NumPy. I'm creating alias NP. And then in pandas, there is a method given to you. Thank you for those guys whoever created this method. It's called read CSV. And in this read CSV, you specify the name of the file, and it's going to read that file. So I have put this file already there. Now let me show you that file. Where is that file? Oh my God, I do not have this file over here. And so what I'm going to do, let's see, let's go to desktop. Let's go to Ashwini stuff and code stuff and temp and maybe this one, and there you go. All right. Paste this file over here. Okay. So this is the file Ohm's law. So let me just show you what's inside that file. Okay. I'm just, I'm going to open with a notepad. We are all familiar with notepad. Okay. In this file, you have voltage, comma, current. And 6, 2, 3, 1, 1, 0.3, 4, 1.2. Basically, these are values. So the first line is telling me, it's an instruction, it's telling me that the first value is going to be voltage, comma, the next value is going to be current. So first value is voltage 6, and my next value is 2. Voltage, current. Voltage, current. The reason this file is called CSV is because it's a comma separated values. You see, every value is separated by a comma. That's why it's called comma separated value file. So this one, CSV, it means comma separated values. All right. And let me run this. It means comma separate values. So you're going to see a lot of time people say, hey, send me the CSV file. Or, you know, when they ask you to send the data, they're going to, this is the terminology they use. This is the language they use. Send me the CSV file. So somebody sends you the CSV file. That's where your data is, ohmslaw.csv. And what's inside this CSV file? These are the contents. Simple. This basically I made this content. Okay. In reality, this is going to be very big file. You're going to see like voltage, current, maybe thousands of values over here, or maybe millions of values. And you're going to have many columns over here. All right. By the way, if you want to see a CSV file, let me see if I have one that I can pull up real quick, just in case some of you are wondering. Temp. Let's go to this, and let's go to data analysis. Let's go to this, and let's go to not this one. Okay, so if I come across the CSV file, that actually has many. Oh, there it is. Data. There you go. Data analysis. Pull down merge customers. So let's see. Sales tab operator 325 kilo. Nope, not this one either. So yeah, if I come across a CSV file that's really big, I'll show you. And okay, see, this is a CSV file. Okay, see every value, see transaction ID, comma, customer ID, comma, this, comma. These are column names, and these are the values for each one of them. So your CSV file will look something like this. And by the way, this is going to be very long. Okay, this is not going to be simple, depending on what type of data you have. Okay, all right. So this is my CSV file. By the way, you can some of you actually who actually are computer background, you might know that you can open this file in Excel too directly. So if you come back to this data right here, okay, and right click, and you says open with, and you can select click on Excel, open with Excel. So if you open with Excel, Excel actually gives you the ability, and that it actually automatically detects that comma for you, and it actually separates this nice and neat in different columns. You see that voltage and current is able to do it for you because automatically Excel is detecting those comma for you, and it's getting rid of the comma for you. And see, voltage is 6, current is 2, voltage is 3, current is 1, 0.3, and so on and so forth. So this actually Excel takes care of you. But reality is this is going to be a text file. Okay, this is a text file. Okay, coming back. Okay, so I read my CSV file. I read into data DF. DF is a short for data frame. So read into data frame. Data frame. All right, and let's print out my data frame. I just want to see what's there. And wait for it, and there you go. You see that it prints out everything. But let's say, oh, by the way, I want to show you something. Let's say I print a wrong name, ohmslaw2.csv. I want to show you the error, and you're gonna get an error now. There you go. You see that it's gonna throw all these error. It's gonna say no such file or directory. All right. Oh, look at that. The mistake I made was I wrote 2 over there. I should not have written 2. I should have written down this Ohm's law. And then I print my DF, and it prints out my data frame. This is my data frame, voltage, current, and so on and so forth. Okay, this is my index right there. This is an extra number that actually is telling you, like, you know, the index of each and every record. Okay, so I got my DF. Great. Now, what do I do with this? Okay, I convert my values into NumPy array. All right, let's do that. So come over here. Next step. Oops, what happened? What did I do? Control C, Control V. Thank God, Control C, Control V working. Thanks to the creator of copy and paste. So I have to do less typing. All right, so I convert. Now I take this whole voltage, all this thing, and I convert into a NumPy array. Remember how I was converting into NumPy array? I was using this right there. Remember that? Right there, you see, I took a list and I converted into NumPy array like that. I'm doing the exactly same thing. Okay, so I converted my data frame. Okay, my data frame is there, and I'm taking this column right there, this column, which is DF voltage. I can actually read one column at a time too. Let's say I only want to read one column. I want to read just the voltage. I can say like this DF. This is the syntax I'm going to use, DF and voltage. Okay, so when I say DF voltage, let me comment this line out. So this way, well, you know what? Let me put a little separator in between. Print and put bunch of octothorpe. There you go. Okay, so I'm printing my DF. It's going to print this. Then I'm going to print this characters, which is a separator. I'm just putting some separator. Then I'm printing just my column voltage and see what it does. You see that it prints this, okay, which is this statement. Then it prints this, which is right here. Oh, which is right here. And then I print just my voltage, which is 6314, which is this right here. Okay, this column. I just print this column out. Okay, so I can isolate just one column. Now, once I got my one column, I can convert that into a NumPy array, right? This is the way to convert np.array df voltage. Okay, np.array, if you remember, there I use np.array. Okay, how can we open a, oops, somebody asked me a question. Let me see if I can. How do I, okay, how do I open this thing up? Oh, oh, oh. Raj Kumar is going to approve. Okay. All right. Okay. Oh, what just happened over here? Raj Kumar, what you just did? Okay. Then, oh my God, what just happened over here? Tap annotation, right? Okay. Where was I? Yeah. So I convert this whole column, this whole thing into an array. Likewise, I took my current and I converted into an array. Great. Now I can just keep doing what I was doing up there. You see, remember how I was calculating my voltage and all? So basically, just I'm going to take these values and just calculate voltage. So apply the same thing what I just did. Define my resistance, calculate my this, and print out my resistance. So come over here. Okay. So I define my voltage. Voltage is basic, sorry, I define my resistance function, and it takes a parameter as voltage and current, and returns voltage divided by current, and your resistance is R equal to resistance V comma I. Okay, your V is this value, this whole thing. Your I is this right here, and then I'm rounding it off. Okay, I'm just rounding it off. Let's say I don't round off. Okay, let me just show you what's going to happen. And then I print my resistance. Okay, resistance R, and let's see what it does. it prints out my resistance 3, 3, 3.3, 3, 3, 3, 2.2 for each one of the values. So it's calculating for each one of the values, okay, and it's printing out my corresponding resistance. So basically, what it did was this. It took 6 divided by 2, and the answer is 3. Okay, 3 divided by 1, whatever the answer is. 1 divided by 0.3, 4 divided by 1.2, 12 divided by 4. So it basically did all this calculation. Okay, it did all this calculation, and the answer came out to be 3, 3, 3.3, 3.3, and so on and so forth. And I realized, you know what? I don't like this. I want to round off my numbers. So let's do round off. So you can use np.round r comma 2. And basically, I'm taking my r variable, which is this variable, and I'm rounding off by 2 digits. Okay. Okay. All right. All right. So I'm rounding off each one of them, and then I'm printing my resistance again. And now it prints out everything neat and nice. Okay, neat and nice. So this is how I'm able to calculate my resistance. Okay. So I got my resistance. Now you know how to read a CSV file. You know how to do computation using this little syntax. Okay, this is all I'm doing. And then you can apply any formulas over here. This doesn't have to be just resistance. This can be anything, any complicated formula. You can use any one of these. Okay, any one of these. Your data can be like it can be big data. Okay, now you read your data. Now let's say you did this calculation and you want to save the result. Oh, let's do one more thing. Now let's say you want to do some more stuff. So somebody had asked me in the just a minute ago, why do we use NumPy? I mean, why are we using NumPy? Why can't we use Lisp directly? Well, here's your short answer. Let's say I want to calculate the mean value of my resistance. Okay, I calculate my resistance. Now I want to find out what is the mean value or variance or standard deviation. You can do all that. So how do I calculate my mean value? I say mean equal to np dot mean r, and that's going to print my mean value of my resistance. You see that 3.08 is my mean value. What if I want to calculate standard deviation? Well, you can print that too. You can come over here and say standard deviation. Excuse me. Standard deviation equal to np dot std. Maybe, you know what, let's say I forgot. Okay, I'll tell you what happens in real life nowadays. So let's say, because there's no way you can remember all these commands, okay, this is going to be so much. So let's see if this command is going to work. I don't know, I forgot, let's say. So I print a standard deviation now. Standard deviation. And let's run this and let's see if it works fine. Oh, look at that. NumPy has no module, no attribute called standard deviation. Now what I do, I actually use these AI tools, and feel free to use AI tools. So you can actually just say how to print, or how to display, how to print standard deviation using NumPy. And it's going to give you the syntax. All right. And well, so here's the code. Well, where's the code? It did not print. Oh, look at that. Empty cell. Oh, maybe it did over here. Oh, there you go. That's it is. So the way you print standard deviation is using this command, sp.std. Okay. So as of today, when you use, you have this AI tool available at your disposal. You don't have to remember everything, but you have to know what you are trying to do. That's important. So focus on what you're trying to accomplish. So I need standard deviation. So the command is std, standard deviation. And now if I run this, it's going to work just fine. You see that? So it gave me standard deviation for my resistance. Now let's say I also want to do the variance. Okay. Well, you can calculate variance too. So let's say my variance equal to NP. And now I think the answer is var. I believe that's what it is. But let's see. Let's print out my variance. Let's see if it works. Okay, np.var. Var is short for variance. And I think that's what it is. I could be wrong. And let's find out. Oh, look at that. I am right. Oh my God. At least once in my life, I'm right today. Okay, so this way I calculate my variance. And this way you can calculate a bunch of other statistics, okay? So NumPy gives you the ability to calculate your variance statistics for this value. So the mean value is 3.08, standard deviation is 0.312, and my variance is 0.09. And likewise, you can calculate your 25th percentile, 50th percentile, 75th percentile, and bunch of other statistics, okay? Minimum value, maximum value, and you can do a lot many things with this. Okay, back
Sir,
to...
sir, I have a question. Sir, these np.var, np.std, these are library files, isn't it?
Yes, they are.
So I have to remember so many library files. So
And
instead of remembering so many library files, I can do 1-2 lines of coding.
yes, so what you can do is, it depends on your line of work. If you in your line of work, you have to deal with standard deviation, mean, and variance, then you're going to be using this function so many times that automatically you'll end up remembering them. So you don't have to worry about that. But if in your line of work, you never use standard deviation, you don't use mean or variance, then you don't have to remember all these commands. Just be aware that there are tools available, and there are tools available. Hold on. Okay, there are tools available that will calculate it for you. You just have to know this part. That's it. You don't have to remember the syntax. And as I was explaining, you can always go to these open AI tools. There are a lot of artificial AI tools available. You can, let's say, today I want to use a black box. Let's say black box is one of them. So you go to black box AI, and you can type your question. You have to sign up for the account. It's free. And you can type this question over there. You can say, hey, what is the command to find the mean value in NumPy array? Okay, that's the question you can ask. What is the command to find the mean value in NumPy array in Python? And hit enter. Now look, I made a mistake. I even did not write my Python right, okay? And it tells me the answer is mean right there. That's the one. So today we are living in a world we really don't need to know the programming language. You just have to know the right question to ask. That's the important. That's what the prompt optimization comes. That's where the prompt comes, okay? So coming back to this, you just ask this question, and that's going to tell you the mean value. This is the syntax to calculate mean. Okay, I got my mean now. Great. Now I want to save my result. So I remember I calculate my resistance, right? This is my resistance. So let's say I calculated like 100,000 resistors. There are 100,000, 1 million, 1 crore, it could be any number of records. I want to save the result somewhere. So you can save it in a CSV file. So I can create another CSV file. And the way you do this thing is simple. Thanks to the pandas, I'm going to use this command right here. So what I'm going to do is come back over here. And now I say df resistance equal R. Basically what this command is doing, it's creating a new column in my df. Remember this df right here. It is taking this df. And this df had two columns, voltage and current. Voltage was one column, and the other column is current. Okay, voltage and current. This is how I'm able to access my column names, this square bracket. Now I can create another column over here, and I'm creating another column by using this little syntax right there. It's very simple. Just say df quote resistance quote equal to R. Now if I print my df now, let me just comment this line out. Now if I print my df, you're going to see this resistance column. Okay, you're going to see this resistance. Let me print this out if you don't believe me, and there you go. You see there, resistance column right there. It has come over there. So for this voltage, this is the current, and this is my resistance. For this voltage, this current, this is my resistance. This voltage, this current, that's my resistance. With this voltage, this current, this is my resistance. They did all this for you. Okay, great. You've done this thing. Now you want to send this to your friend. Okay, maybe your professor, or maybe somebody that asks you to calculate resistance based on the voltage and current. Okay, you can save this in a CSV file now. And the command is, if you're guessing that to read a file, if the command was read CSV, then to save it to a file, the command should be to CSV. And if that's what you guessed, you are absolutely right. So the command is df to CSV and type the name of the file. I'm calling it junk because I know how to calculate resistance. And now I had to do all this work for nothing. So I'm going to call it junk.csv. Index equal to false. So I'm specifying this parameter because I don't want to be sending this data 0, 1, 2, 3, 4, 5, 6, 7. Okay, this is irrelevant to me. So this is called index right here. I don't want to send index. So say index equal to false. And now I run this command. Now when I run this command, you will see a junk.csv appear. If I come over here, you can see there is no junk file. Okay, you don't see the junk file right now. But now when I run this command, you're going to see a junk file appear over here. So let's run this. And there you go. Okay, now if you come back now, you're going to see junk right there. You see that created just now 11/16 on this date. All right, let's open this file. Oh, there you go. Open with. Let's open with Notepad. And there you go. You see that voltage, current, and resistance. Voltage is 6, current is 2.0, and your resistance 3.0. So you see 3 values now. Okay, there are 3 headers: voltage, current, resistance, and 3 corresponding values. All right, great. Now you can send this to your friend or whoever asked you to calculate resistance based on the voltage and current. Okay. Now,
Sir, again, to be on lighter mode, these things we can do very easily in Excel as well, na? Instead of so much length of
yes, you can. Yes, you can do in Excel. And because this is a course on Python, that's why I'm showing you to do in Python. But I would favor more Python, less Excel, because Excel has one little problem. If your file is very big, let's say somebody sends you data, and that data is maybe like 50 megabyte or 60 megabyte, and you try to open that in Excel, your Excel will crash. I mean, it's gonna, well, I shouldn't be saying crash, it's gonna be very slow, because Excel is very ideal, is very well suited when your data is small. Okay, but if your data is, let's say, in gigabytes, actually try opening up a gigafile. You know, yesterday or day before yesterday, I was teaching one of the class, and let me see if I can find that. I was trying to open one of the file that was in megabytes, and it did not open up. It actually took a long time. So let me see if I can find that file and show you. Maybe this. Not this one. See, this is a small file, 226 bytes. But sometimes you come across this CSV file that are really big. So not a big file. Not a big files, yeah. So over here, I don't have the example right now, but sometimes you come across this. Look at this Ohm's law CSV file, only 1 kilobyte. So you can open this in your Excel, and great, it's going to work. But if your file is, let's say, 50 megabyte, okay, so like thousands of millions of records in it, then your Excel file will fail, right? I mean, not fail, but it's going to be very painfully slow. And then you're going to be wishing that I wish I knew, or I wish I know somebody who can actually solve this problem for you. And this is where your Python shines. Python will take a gigabyte like type of file, and it's going to happily do that for you without any problem. I hope did I answer your question? Why would you use Python over Excel?
Yes, sir. Nice answer.
Okay, so your size of the file, that's the number one thing. Okay, all right, back to this topic now. I lost my chain of thought. Oh yeah, so see
if you when we actually creating CSV file, sorry sir, I'm audible.
Yes, you are.
Okay, when we are creating CSV file, then when in which directory it will be saved? Can I save in any drive or in?
You can save it wherever you want. I actually saved it on a current working directory right now. I just saved it at current working directory, and then I can just copy and paste and send it to anybody. So if I want to send it through WhatsApp group, and let's say I want to send it to you right now, and let me see, since I'm part of the WhatsApp group right here, am I? Yes, I am. So I can just come over here, and I can just say attach, okay, document, all right, and go over there. Where is that term? And there you go. and to NumPy application, and then there you go. And now I can send it. Okay, and I can send it to anybody now. Okay, and let me move this over here, and there you go. So it doesn't matter what drive you can save. I mean, you can save it in wherever you want. That's not a big deal. You can just copy and paste. Let's say if it's saved in your current working directory, just copy and save it over there. Okay, so see, now the file is there. All right. Okay, now where was I? Yes. Now, next topic now. So now you know how to read a CSV file. You know how to actually, this is the real world scenario, by the way. You're going to be reading CSV files. How to do computation. We did some computations over here. Okay, we did some manipulation with the data. And then once we got a result, we can store the result in a data frame, and then we store it in a CSV file. And now you can send the data to whoever you want to. Okay, index equal to false means that I don't want this 0, 1, 2, 3, 4, 5, 6, 7 written over there. That's what index equal to false means. I just got this question from somebody. And so I apologize. I've been noticing there are a lot of questions, and I try to answer those questions. But sometimes, I mean, I don't know how to actually see those, how to see those questions again. But if I'm able to read the question, like sometimes the question disappears when you ask me the question. So as I'm reading, it disappears. So I'm not able to read the whole question, and so that's why I'm not able to answer. But if I'm able to read your question fully, then I'll answer your questions. And apologize in advance if I'm not able to answer all the questions. So yeah, that's why you type index equal to false, because you don't want 0, 1, 2, 3, 4, 5, 6, 7 written over there. And for your experimental purpose, remove this index equal to false and see what it does. If I run this now, and if I go back to that directory, now if you look at this junk, you're going to see that 0, 1, 2, 3 written over there. So if I open this, and like there, and there you go, you see that 0, 1, 2, 3, 4, 5, 6, 7, unnecessary. I don't really need this thing. So that's why I put index equal to false. Okay, now, where is that? Okay, so got this. Now, let me close this now. All right, now let's say you want to have interactive. Okay, so there is a lot of tools available. You can actually make it interactive too. So on this, my Jupyter right here, on this Jupyter, I cannot make it interactive. I tried it, and this one did not work on my laptop. But the reason it did not, sometimes it may work and sometimes it may not, is because you have to install a widget. And if that widget is not installed, then it's not going to work. So there's something called IPy widgets. I installed this IPy widgets, and I tried to run this just to see if it's going to work. And it did not work. Okay, so let me see. So the another solution is use Google Colab. So let me show you what I mean by this. Come over here. This is my Google Colab. All right. And oops. How do I? All right. Code, paste it. And let's run a simple function. Basically, I'm checking that can I interact with my code. So basically, you know how we were changing our X values? What if you can change your X values on the screen itself, like using a graphical user interface? And Google Colab and your Jupyter, it does give you the ability to do all that. And see that right there. Let me remove this. You see this? So as I'm changing this value, okay, you see this number is going to change. So see, number became 2.3. Number became 1.3. So these numbers have changed. And one of the coolest thing about this is that now you can actually do your computation. You can do all your calculation by selecting your X and Y values from here. Okay. So by, let's say you're calculating resistance. So you can put your voltage over here. You can put your current over here, and you can change your voltage and current. And as your voltage and current is changing, you can see your resistance change over here. You can see that visually. So that's one of the good thing about this. That's one of the a very handy tool. It's called IPy widget. So let me show you. So this is one of the IPy. Oh, not this one. Sorry, right there. So first I test, like, can I do this thing? And on my machine, I could not do this particular stuff over here. So minimum 0, maximum 10, step is 0.5, value equal to 5. So let's see what this function does. By the way, you don't have to remember all these syntax. You're going to go crazy trying to remember all this syntax. You can just ask you can actually look at the documentation for your IPy widget, or you can ask any one of these open AI tools, and they can actually generate the code for you. So in this case, I'm saying my minimum value is 0, my maximum value is 10. So if you come back to this right here, you see that. Let me just run this code again. And there here you go. You see, it goes from 0 and all the way up to 10. You see that? 0 to 10. Okay. Now, what is this 5? Oh, where is that? This 5 tells you the default value. So when you run your code, what is the default value you want? You want 5. So when I ran my code, you see it gave me 5 by default. That's my default value. What is the step 0.1? This actually tells you that when you increase or decrease, always increase or decrease in a step size of 0.1. That's what it means. All right. So I got this. Now let's calculate an Ohm's law. Let's create an Ohm's law calculator. Okay. So I create this, copy, come over here. Oh, sorry, come over here, and let's create another cell. So, yep, right there. Another cell appears over here. Paste that code. All right. Now this is a little bit complicated code, but basically, let me just show you what it does, by the way, first. And there you go. So this is my Ohm's law, and this is my current. This is my resistance right here. So by changing my resistance by manually, like by using my graphical user interface, using my mouse, I can change my voltage. Right now, my current is 2. My current is 2 amperes, and my resistance is 5. So my voltage is current times resistance. So my voltage is showing you 10. And you can see the red dot right here. This is my point, red dot. So my current is 10. Sorry, apologize. My current is 2. My voltage is 10. So if my I, oops, sorry, where is that? Yeah, a voltage is 10. So now let's change my current. I'm going to change my current to 4. So come over here and make it 4. There you go. I changed it to 4. As soon as I change my current to 4, my voltage has been changed to 20. Okay, because 4 times 5 is 20. All right, let's change my resistance. I change my resistance to maybe, let's see, 40. Okay, my resistance is 40. So my current is 4, my resistance is 40. So 4 times 40, and the answer is 160. So my voltage is 160 right there. So this is a pretty neat little handy tool that allows you to calculate your values using this graphical user interface. So this way you can actually change, let's say your this over here, you can manipulate, you can change over here, you can calculate all types of voltage. You change your current, change your resistance, and it basically calculates it for you. So you can see visually how your values is changing. Okay, so real quick now, if you understand this, this is basically a scale. I'm scaling that function over here. So you see, I call interact right there. I'm calling my interact. Just like over here, I call my interact. So I'm specifying my test function, and I'm specifying my these values, like what exactly my argument should be. All right. So that's what I'm doing over here. I'm specifying my function, which is Ohm's law. Okay, Ohm's law, this function, and then in this function, I'm specifying my parameters. This is my I and R. So I'm specifying my I and R. I'm saying float slider, and I'm saying that, hey, this, and then I'm specifying my value, minimum to maximum, step, and so forth. Okay, and then this one right here is basically plotting this graph. Okay, that's what's happening, is plotting it. So that's all it's doing, is plotting this graph. So print voltage, this print over here gets printed right there. Okay, and I print my voltage. Then this is my scatter plots using matplotlib, and it plots all this thing for you. Okay, so this is just there's a lot of code happening over here, and if time permits, then I'll show you how to use matplotlib. So this will explain you this particular code. Basically over here, I'm just plotting this line. Okay, so I'm saying that plot.figure size 6,4 means 6 width and length. Okay, 6 and 4. Scatter plot, I'm using scatter plot, and my x value is I, my y value is v, and my color is red. My label, your point. So label is right here, your point, and my what is that? Color is red. So this is red. Okay. My X label, my Y label. I'm putting my X label, Y labels, current and voltage. So current and voltage as my X and Y label. And then I'm putting my title. My title is Ohm's law V equal to IR. Ohm's law V equal to IR. And then I'm just adding a line. All this thing, I'm just prettifying my picture. That's all I'm doing. I really don't need all that. I can just, put like this line, this grids. These are called grid lines. So I'm just adding these grid lines. Okay. So I'm just creating each one of them. There you go. Grid equal to true. And you can remove this. And that's grid is going to go away. All right. So what I would do is, what I would suggest to you students is play around with the code a little bit. Okay, so this will, by playing around, you have a better understanding. By looking at the code, you get a little idea, but you will not get that the level of understanding unless you play around with this thing. So just play around, try to see, okay, what if I change this? What if I change that? And this will help you understand. And when I create code, I don't create code within 5 minutes. It's not done. It doesn't work like this. It takes time. So this is going to be trial and error. All right. Okay. So this actually creates that widget. So this is something I want to show you, that you have this option available for you. All right. Now let's look at some practical examples. Cantilever beam deflection. Let's say you are working on a problem. I'm sure some of you who come from a mechanical background must have heard this term, cantilever beam deflection. The cantilever is like a diving board. Basically, it's a board like this. And when you are applying no force, it's basically straight. But when you apply some force on the end over here, it's going to bend a little bit. Okay, it's going to bend. And that bend is going to be, let's say, Y. Now, clearly, if you're looking over here, this bend, like this distance is going to be a lot larger than this distance, than this, than this. This is going to be a lot smaller. But this, let's say, is Y. Let's say your deflection from your vertical, the deflection or the vertical distance of your board from this point, that depends how far it is from here. Okay. So if you are very far from here, let's say you are over here, your Y is going to be very high. But if let's say you are over here, your this Y is going to be very small. So clearly your Y is a function of X, right? Well, thankfully, I don't know who came up with this formula, whoever did, or maybe we should thank him, that he said that your Y is equal to this. This is your function. And Y is equal to F times X to the power 2 times 3L minus X times something. Now, you don't have to remember this formula. Just be aware there's a formula like this. And by the way, if you write it down on a piece of paper, this will look something like this. It's going to say, or it should be like Y equal to F times X square times 3L minus X, and then divided by 6 times E times I. All right, so that's your formula. Okay, so this formula is this one. So F is your F multiplied by X to the power 2, so X square, all right, times 3L minus X times 3L minus X, and then divided by 6EI divided by this thing. All right. So this is your cantilever formula, the cantilever beam deflection formula, and you want to calculate. Okay, now you want to calculate a bend along an x-axis. So let's say what's given to you is the force, and length is 2 meters. Let's say this length from here to here is 2 meters, and the amount of force you're applying is 1000 newtons. And let's say your E is basically Young's modulus. All right, it's given as 2E11. By the way, E in scientific notation, how do you represent? Let's say, on a piece of paper, if you have to write a number, let's say you want to write a number 10 to the power 7, right? You can write 10 to the power 7 on a piece of paper. But how do you write something like this on a computer? Well, in Python, they have come up with this E notation. It's called exponential notation. So you can specify 10, then you can say E7. This is how you write. So you scroll down. Oh, by the way, another one would be if I say 10 E minus 7. This will mean 10 to the power minus 7. Okay, so just be aware of this thing. So you will see this word E. E is like exponent. All right. So I'm saying 2E11, meaning 2 times 10 to the power 11. All right. This is saying 10 to the 1 times 10 to the power minus 6. So your I, which is second moment of second moment of area. Think of this as just a value. It's a value. Okay. Don't have to figure out how this formula came about. Just know that there's a formula like this. Depending on your domain, maybe you may have a different formula, but that's all it is. It's just a formula. Okay. So position along the beam axis. Now what I'm doing is I'm generating some values. I'm saying that, hey, I wanna create me some values. So NumPy allows you to create some values. It generates some values. And how many values I'm generating? I'm generating 100 values. So here, generate. Oh, look at my spelling for generate. Generate 100 points or 100 values ranging from 0 to L. Okay, so it's going to generate 100 points for you. Okay, evenly spaced points for you from 0 to L. What is my L? 2. So from here to here, it's going to generate 100 X values, 100 X values. And let's look at some of those values. Okay, let's see what it generates. So how do you see a value? Print. Remember our good old friend print. And let's look at some of the print statement. And let's use F. Okay, I use my format. So X values. Now, come over here, X values, and then print out my X. All right, so let's run this code, and let me just comment this whole thing out. So you can see step by step what's happening. Let's run this, and there you go. Where is that? Oh, there it is. So see, it generated all the 100 values. If you count every one of them, if you're really bored, you can start counting each one of them. The answer will come out to be total 100. So it generated 100 values for you. 0, 0.02, 0.06, all the way up to 2. So see, it's generated from 0 to 2. Total 100 values. Okay, I got my 100 values now. By the way, let's say you only want to print 10 of them. You can do that one too. You can just say X, then there's a small notation like this, dot 10. And that's going to just print first 10 values. So you can just say X values, first 10. First 10 X values. Oops, it should be called first. Run this, and there you go. This is my first 10 values of X. Okay, 1, 2, 3. Now just printing the first 10 values. And the way I'm doing, I'm using square bracket colon 10. This is a smaller notation. Okay, now I want to calculate my deflection. All right, step number 2, calculate your deflection. Now, what is the formula for deflection? This is my formula right here. Okay, so calculate my deflection. I just use the formula F times X to the power 2 times 3L minus X divided by 6 times E times E. All right, now let's see what it does. Now remember, there are 100 values, right? So it's going to do all the 100. Let's do actually small one. Let's, instead of doing 100, let's make it 10. Let's start with 10, and let's start with 10. Okay, instead of saying 100, let's generate 10 points. And let's calculate my Y. Let's print out my Y. Sorry, not calculate. Print out my first 10 Y values. Y and Y. All right, let's run this and look at that. So these are my 10 values it created for X, and these are my corresponding Y values. Okay, and it applied that formula. Which formula? This formula right here for each one of them. So when X is 0, my Y is 0. When X is 0.2, my Y is 0.0023. In other words, when my X over here goes 0.2 over here, this Y value right here, this vertical Y is going to be how much? 0.002. Likewise, if my x is, let's say, 1.7. If my x is 1.7, my y is going to be 0.0111. So if my x is 1.7, which is somewhere over here, the deflection, this distance from here to here is going to be 0.011, right? 0.011. All right, great. So this I did for 10. Now you can.
I have a question. Like you got the answer in horizontal format. So can I get the answer in vertical format?
Yes, you can. Okay. Now, so I print my first 10 values and I print my first 10 y values. Okay. Now, if you look over here, oh, where is that? I lost that. Oh yeah. Now look at these values now. E to the power minus 0.6. So basically what this, let's look at this number. What this number is. This is 2.03 and so forth times 10 to the power minus 6. That's what this number is means, okay? Likewise, this number will mean 8 times 1.7, 1.07, so and so forth. E meaning 10 to the power minus 6, okay? So that's what it means. All right, so it prints out all my values. I'm happy with that. Okay, I print my first, got my all my deflection values. Now, what do I do after that? Now, let's say I want to plot them. I want to see how my deflection value looks like, okay? You don't have to do that. You can stop right there, okay? Maybe you understand what's happening after this. And you say, you know what, I really don't care. I don't want to plot it. I'm happy with this thing, and you're good. So this is where you can just stop right there, okay? Or let's say you're feeling adventurous and you're very inquisitive and you want to say, you know what, I want to plot these values. So let's do that now. So what I'm doing, I'm generating. Oh, where was I? Oh yeah. So first I create my plot, okay? Figure size. I specify my figure size, 10,4. And then I plot my original undeformed beam. Now remember, when you are plotting your original ones, which is right here, this is your original. I want to plot this first. All right, so I'm going to plot this. And let me remove all this. Let me comment all this thing out. Okay, so I want to specify my figure size. Now, when you plot something, remember you have to specify x and y values, right? So my x value is this right here, x, which is this one, the 100 points I created. And what is my y value? Well, if you think about it, if you want to plot the original, your y value should be all 0, right? Because there's no deflection over there. It's not going down. Your y values are all 0. So how do you create zeros? Well, one way is you can actually just say over here 0, 0, 0, 0, 0, 0, 0. You would have to write 100 times. That's going to take you forever. Or what you can do, you can have this utility called np.zeroslike. And what it's going to do, it's going to take this np zeros like. What it does, it takes this x value, whatever this x is, and it's going to create bunch of zeros for each one of these x. So in this case, how many x do we have? If you look at this code, this one has approximately, not approximately, I apologize, 100 x's, okay, 100 values. I'm just printing 10 right now because that's all I want to see. I just want to print first 10 values. 100 is going to take too much space. So since I have 100 values of x, I want 100 zeros. So I use this little command, nps.zeros like x. Okay, that's what's happening. And let's say you forgot. There's no way you can remember all these commands. Well, thank God to the creators of human brain, because human brain created these open AI tools for us. So let's use that and ask a question. I have a NumPy array X. I want to create as many zeros as there are elements in X. How do I do this? Give me the syntax. I'm just being a little bit more descriptive. You don't have to be, by the way. So I have a NumPy array X, okay, right? I have a NumPy array X. Oh, where is that? Did I lose that? Oh dear God, did I lose that? Oh yeah, there it is. So I'm saying that I have a NumPy array X, which is right here, and I want to create as many zeros. Remember, when you to draw this thing, you have to draw 100 X points and you have to find 100 Y points. Okay, so I'm basically creating 100 Ys. Oops. All right. So enter, and there you go. It may give you a different syntax. There you go. You see nps dot zeros light. Okay, that's what happens. All right, so I got my Y value. Okay, and then I'm specifying my color, label, and so on and so forth. And let's run this, and there you go. You see, it just printed out beam right there. So from 0 to 2.0. So my Y is all zeros. You see, all Y's are zeros, and my X is all these my points are X's. Okay, each one of them. All right, so I plotted this. That's step one. Now I want to plot my deformed shape. Okay, I want to do my deformed shape. Okay, my deformed shape is what? My X value, right? I want to plot my X value. Let me comment this line out, by the way, now. I want to plot my X value, and I also want to plot my Y value. Okay, so X and Y. And by the way, this one is just a color. It's basically saying blue color, and the line should be like hyphen like this. Okay, over here, I can put a double hyphen. So this is just a simple syntax. All right, let's plot this. And you see that. Okay, so it gave me a deflection, but look at my deflection. It's actually going up. But remember, my deflection is supposed to be up, or I'm sorry. See, it's going up like this. This is my deflection. But ideally, this should not be going up. It should be going down. And the reason it's showing up is because this Y is coming out to be positive. Now remember, we want this to be negative. So what I'm going to do, I'm going to change this to negative, minus. Okay, minus Y to display along the negative Y axis. And let's run this. And now if you come back and you see that now your Y is like this. Now it's going down. All right, now I also want to plot the original one too. Okay, so come over here, move this, and plot the original. And there you go. Oops, sorry, right there. So this is my original board right here. And this is my deflected board right there. Okay, okay, great. Now I got this. And then I realized that, this color, this one is black and this is blue. Maybe they both should be blue, right? So you can actually come over here and change K to B. Okay, K stands for black and B stands for blue, by the way. And run this, and there you go. You see that this is blue and this is blue. So it actually shifted like this. All right, now you want to put some labels. Now look, there is no label over here. It does not say what this value is, what is x-axis, what is y label. You don't know that, right? You want to put some labels over there. So let's add some labels. All right. So my X label is length along beam and my Y label is deflection on meters. Let's run this again. And there you go. You see that length along beam, deflection. So these are my labels. Okay, I added my label. I also want to put some title over here. Well, if you think there's a command called title, you will be right. Title. Let's run this. And it prints a title. Where is that? There you go. You see it prints a title. Cantilever beam, original versus deflected shape. Now, I say, you know what? I also want to put a legend. Now, what's a legend? Legend is basically telling you that what this curve means and what this curve means. Because right now you don't know anything. I mean, you as a programmer, maybe who designed this code, you know right now. But maybe if you give this picture to somebody, they would not know what this line means. Okay. All right. So you add a legend. And what legend is going to do is going to, you see this label right there? It's going to explain, it's going to add that label to each one of those pictures. And let's run this. Right there. Original beam axis, deflected beam axis. Oh, look at that. Both of them are blue. So one blue is the original beam axis, and the other one is deflected beam axis. Now look at these colors. You don't know which one is which one. You don't know whether it's talking about this blue or this blue. Well, that's why, my friends, we actually use different colors. We use K. K stands for black. Now, I can go one step further. I can actually go this hyphen. Okay, run this. Come over here, and there you go. So now it's saying the original beam axis is this one, hyphen, hyphen like this. So this is my original right here. And the deflected is this one. This is my deflected. All right. So I got this. And then you can actually have, you want to see grids? You know those lines over here? Maybe you want to see that too. You're a grid guy. You love grids for some reason. All right. And there you go. There you go. There's your grid right there. All right. You can prettify. So this is called prettification. Basically, you're just taking a picture and just making it look a little bit aesthetic, more, visually more appealing. That's all you're doing. And then at the end, you say plt.show. It shows all this thing. The most important part for you is not this part. This is just to give you a visual. The most important part is you, from a technical background, is this part right here. Just understand what's happening over here. Play around, understand this part. You'll get a better understanding of what's happening behind the scene. Moving on to the next topic. Okay. Now we plot x-axis and y-axis for a series of values. Okay. Let's see. Well, actually, we did that already.
One question, sir.
Mm-hmm.
Excuse me.
Yes, sir.
Why figure size is important here? It is necessary in every case.
Size, you're talking about this size?
No, figure size something 10.4. Yes, yes.
Basically,
10,
if you
10,
don't put it, if you don't put it, then it's going to use the default. So let me just show you. Remove the figure size. Okay, and let me run this code, and you see that where is that? You see, it uses the default. Okay, this is the default one. So I'm actually saying that, hey, don't use the default one. I want you to use. You can actually make it a little smaller. Okay, make this thing. Let's say maybe for some reason you have a microscopic eye. Okay, so let's say you want to make it 2 and 1. Okay. All right, 2, 1 on this, and let's see. Oh, look at that. It became very small. And maybe for some reason you say, you know what? I don't like this small. I want to make it more smaller. So 0.001 and 0.00001. All right, let's see what it does. And there you go. You see, it's there, but you gotta have you're just gonna strain your eye. Your eye is gonna just pop out of your eye socket, trying to figure out where this is. Okay. Okay. So what figure size does? It allows you to control the size of the figure. So you are overriding the default one. You can make this figure size really big, 100. Let's make it 100. Play around, 140. All right. And let's run this code. And let's see, where is exactly it went? Oh, look at that, it disappeared. Oh, there it is. You see that? I made it 100 and it is really big. And it even gave me the scroll right there. Okay, so it's really big picture. And you see that, you look at this thing, the text is there, it's very tiny. You see that it's so tiny. Okay, back to this topic now. So,
what is the default size?
Okay. Default size, I don't remember at all.
No one is there. What happened?
I'm sorry. What happened where? Okay, default size. I do not remember on top of my head what the default size is. It may be different for different Jupyter notebooks, depending on the size of the screen. I do not know the answer for that. And I do not really, I mean, I use default size only if it's, if I'm happy with that, but if I'm not happy, then I use this figure size to maintain consistency. Okay. Now,
Sir, that np.line space, what you have written, np.line space, that is just giving the value of x and y. That's the job of that line.
Where is that? np.line space. Oh, lin space. Okay, it's called linear space. It's a short for linear space.
It is just giving the value of x.
Yes, it generates 100 points ranging from 0 to L. That's all it's doing. It's generating 100 points for you. All right, nothing else. Okay, then where was I? So this one, okay, in this case, let's say you start with just one value. You can even do one value, okay, if you want. All right, so there is that. And all right, now plot the why is the vertical bend at it? Okay, I did this, and this is basically same as the top one. And what I'm doing is let me just move this up. Okay. And then I come over here, show me the bend along x-axis. All right. All right, next step, optional. Now comes the question, can we have this interactivity? Remember how we did all the interactivity that we were doing? Can we do something like this? And remember, this comes at a price. Not all these types of interactivity can be nice and neat. So let me just show you this particular code and come back to this Colab. Okay, and let me run this now. And let's see how exactly it plays out. Okay, force, length, and E. Okay, this is my cantilever right here. So let's see if it works. It does actually work a little bit. All right. So you see that by changing this force, length, and E, you can actually see how the values are changing over here. Okay, deflection, how the deflection is changing. So let's say my force is very high. Okay, let's say my length is actually length is very high too. Let's make my force very high. Okay, my force is high, my length is very high, and you can see deflection, and you can see, and let's say my E, elasticity, is very low. So you can see it's changing a lot. Okay, your length along beam, it should see it's going up to 2. It should not go beyond 2. So you, hello, could you? Okay, I've been hearing a lot of background sound. I'm gonna mute you guys out. All right, thank you. Okay. So, all right, so there is this now, all right. The most important part is interactivity is more like, these are like bells and whistles, okay? They are not like, for technical guy, for you who is trying to see the data and you're just trying to analyze your data, then interactivity can help you somewhat, but not a lot. And for me, the most important part that I would focus on would be right here, this one. This part, where is it? This one right here. Okay, this part right here. This is the most important part because this is one actually is where I'm doing all my calculation. So understand this part, and this is just a visual representation of what you're doing. That's all. Okay. Now, let me move this over here. Okay, got this. Now comes curve fit. A lot of times what happens that, let's say you're doing an example. Okay, you're doing an experiment, Hooke's law that everybody has seen. And you're an engineer and you measure the extension of a spring under different load. So you are taking a spring and you're seeing how does your spring bend under different load, like how much it stretches and not stretches, so on and so forth. And you want to determine, let's say he wants to see if the Hooke's law is really valid. Okay, you're just trying to see if this Hooke's law is a whole. We know Hooke's law, what that is force equal to kx. So force and extension should be linearly related. That's what the Hooke's law says. But let's say you don't know this part. Okay, you're trying to maybe you know, but you're trying to verify that if the Hooke's law is true. So how do you do something like this? Well, we know that the extension is proportional to the force, right? Intuition tells us that the more force you apply, the more your extension is going to be in your string, right? In your spring. So we know the extension is equal to A times force plus B. So this is a simple formula. If you know your extension, if your X is proportional to force, what it means is that X can be written as A times force plus B, right? This means this mathematically, all right? Okay. So I'm saying my extension X equal to A times force plus B, all right. And then you try to find the value of A and B. For your Hooke's law to be valid, okay, for your Hooke's law to be valid, what exactly is the relation between X and F then? Well, your X is equal to 1 over K times F, right? In other words, I can say X is equal to 1 over K times F plus 0, right? So this, the equation I just showed you a minute ago, where I was saying x equal to AF plus B. So for this equation, okay, we want to make sure, we want to find our B and we're going to find our A. And our B should come out to be 0. Now we're going to find our B through experiment. We're going to do some experiment, and that experiment is going to show us that our B is 0. Once we determine our B and once we determine our A, that will, this will give you a verification of your Hooke's law. You'll be like, okay, I'm satisfied with my Hooke's law. That makes sense. And let's do that. So let's say you do an experiment. Okay, this is your, you do an experiment, you apply some force, and you apply 0 Newton, 2 Newton, 4 Newton, 6, 8, 10 Newton of force. And you see your spring. And these are the extensions in your spring. By the way, this is real data. Okay, and this is the extension that happens in your string. So when you apply 0 Newton, the extension is 0. When you apply 2 Newton, the extension is 1.1 millimeter. You apply 4 Newton of force, the extension is 2.1, and so and so. Reality is you're not going to get data like this. You're going to be getting data in a CSV file. I think I showed you before how to read a CSV file. So let's say you read a CSV file, you got your data, and you got your force and extension. All right. The first thing you do, you are trying to form this equation, right? Extension equal to A times force plus B. So since you're trying to form that, you're trying to determine the value of A and B. There is, in your NumPy, thankfully, there's a function called polyfit. And what it's going to do, you give this value of this variable force, okay, you give this variable force, and you give the variable x. Okay, you supply all this force, supply this x, and then you supply what is the degree of this polynomial. And the degree is 1. Okay, so inside the polyfit, you specify your force, you specify your extension, and then you give your degree 1. Oh, can we take a break of 5 to 10 minutes? Yes, let's take a break. So let me just finish this real quick. So coefficient equal to NP, polyfit, force extension, comma 1, and then you print your slope and intercept. That's going to print your slope and intercept. All right, let's take a break for 10 minutes, and let's convene at 12:15. Is that okay with everybody? Actually, aren't we supposed to take a break? Yes, sir. Okay. What is the schedule? Could somebody inform me what's the schedule for break? Like how long are we supposed to take this break for? All right. Okay, so let's convene in 15 minutes then.
Hello, sir.
Yes, sir.
Can you please share this notebook in WhatsApp group or Google Drive?
Sure.
The previous one you have completed so far.
All right.
नीचे रखो जो सामान है वो ले आना आगे रहने दो।
Hello, good afternoon. Welcome back. Am I audible?
Yes, sir,
Yes,
you're
sir.
audible.
What is?
Yes.
Thank you. All right, thank you. Okay, so I hope my screen is visible too. So let's come over here. All right. So this is your cantilever deflection. All right, moving on to the next topic.
Sir, I think your
Deflection.
screen is not visible.
Oh, okay, thank you. Let's see. All right. Is my screen visible now?
Yes, sir.
All right, thank you. Okay, now you have cantilever, curve fit. Now let's move to a curve fit, okay. So let's say you have curve like this, okay. Let's come over here. So let's say you have, so basically what I'm doing, I'm calculating this value, A and B. So the way I'm calculating A and B is I have read my value of X, okay? My X value is read. Sorry. So my X is equal to A times force plus B. And because my X is equal to A times force plus B, and I have read my X, okay, these are my readings, okay, X readings, and my force readings are these. So based on my force readings and my X readings, I want to calculate my A and B. And thankfully, there is a function called polyfit. It's basically short for polynomial fit. And what it's going to do is going to take all your force values, it's going to take all your extension values, X values, and it's going to produce a polynomial of degree 1. Okay. Give me a second. I'm getting a lesson message. Let me just. All right. So where was I? Okay. Now, X equal to A times force plus B. And cantilever, where is that? Oh, not a cantilever, sorry. Perfect. So now it's going to produce my polynomial. Now, how do you define a 1-degree polynomial? Now, if you remember from your high school math, what makes a degree 1? The only thing that you need in a 1-degree polynomial, let's say if I define a polynomial, let's say, let's come over here. Let's say the polynomial is 2x plus 5. Okay. This is a 1-degree, right? Another 1-degree could be, let's say, 3x plus 1. Another one could be y equal to 6x plus 7. So in this case, you're 2 and 5, 3 and 1, 6 and 7. These are the only numbers you need, right? To define your 1-degree polynomial. You really don't need the x. X basically is implied. So this polynomial I can write like this, 2, 5. This 1-degree polynomial can be written like this, 3, 1, right? This polynomial can be written as 6 and 7. So that's what's happening over here. That's what's happening over here. This one is calculating. Oops. This one is calculating my A and B. Okay, so my A is 0.505. It's calculating those two pairs. Okay, so slope and intercept. So it's calculating my A and B. And once I know my A and B, so my polynomial is 0.505. So my X is going to be 0.5, which is this value, plus my B value. My B value is 0.03. So it has calculated the A and B. It has calculated this A and this B for me. So this function has calculated my A and B. Once I know my A and B, so based on the above data, I can conclude that the relation between A and B is x equal to 0.5 times x plus 0.03, or you can just simplify this a little bit further and you can say f equal to 2x minus 0.06. Now let's look at this value a little bit more. Okay, let's come over here and let me run this code. And there you go. So this is my value. All right, so my formula now is this. This is my formula. But is it a Hooke's law? And if you think about it, it is a Hooke's law. Let me change this into a markdown cell. All right, so this is almost a Hooke law. And this term, look at this 0.03. It is negligible compared with this term. Now look at my 0.5 and look at my force. Now look at my force value, 2 Newton, 4 Newton, and look at my extension in millimeters. Okay, so if you let's rephrase, let's rechange this equation. So when you change this equation, it's going to turn into something like this: f equal to 2x minus 0.06. So come over here. So f equal to 2x minus 0.6. So if you look at this term, this is a very negligible term. It's very tiny. So this term can be safely ignored. All right. And the reason it can be ignored is because in a grand scheme of things, this term is having a very negligible effect on this whole term. So your Hooke's law, okay, since this number is very small term, so your Hooke law is holding. And this term gets introduced because we are doing measurement. Remember, we are doing measurement. So when you do physical measurement in real life, you will come across a little bit of noise. So this is called a little bit of error, a little bit of noise. It will always happen. And that noise is this right here. So you keep doing this experiment time and time again, and you're going to see this number is going to be very tiny. It's going to be 0.06, 0.04, maybe it's going to be 0.0001 maybe next time. So these are called noise. So this noise can safely be ignored because it's a very tiny value compared with 2 times x. All right. Where was I? Now let's plot this curve. Okay, let's try to see. Now remember, we plotted this. This is your equation of a line, right? But look at this equation. Isn't this equation of a line y equal to mx plus c? We all studied in our high school mathematics. So this is an equation of a line. Let's try to plot this equation of a line. And also, let's plot these points. And let's see how they look like. Let's see how they fare against each other. So come over here and scatter plot. So first I'm going to plot. First thing first. Let's draw the scatter plot first. All right. So I'm giving my force, I'm supplying my extension. This is my force and this is my extension, right? These are my force, this is my extension. I'm supplying that and I want to plot that. And there you go. So see my force and extension. These are my data points, okay? Data points. Oh, look at that red color. I don't like red color. That's just scary to me. Danger. Let me change it to color. Right? Okay, green colors. I like green colors. So you got this. Okay, these are data points. Now I want to plot this line too. Okay, I want to plot this. So how would I do that? You remember you need your x and y value, right? So you can just say, just add this line of code. Come over here and add this line of code. Now this is my x value. This is my y. This is my x value, force. My y is this right here, predicted extension. Now look, this is my curve, right? So my y is basically my f. So I want to find my f. So how do you find my x? How do you find that value x? Well, I'm actually using this little function called right here, predicted extension. So what's happening is that behind the scene, I'm calling this one more time, okay? Actually, I'm sorry. I'm calling this function poly1d and I'm supplying this coefficient. So I'm supplying my a and b. So as soon as I supply my a and b, this function gets created for me. Okay, this is the function that actually creates this function for me. So once I got this function, then inside this function, I'm giving all my okay, Villager Jahan is asking to annotate the shared content. Okay, let's see. What do they want to annotate? Okay. All right. Okay, sir, are you trying to annotate? All right, I'm gonna remove this. Okay, so what I'm doing, I'm taking these values A and B, and from this A and B, yes, sir. Did somebody ask me a question? Okay, no question. So I'm taking my A and B, coefficient A and B, that's determined from here. And using my A and B, I'm trying to forming this function. So this creates the function, okay, using my A and B. So it creates this function for me. Once it creates this function for me, okay. I got this X function. Now I can make a prediction. So I can say fit function force. Now I can apply this F into that, okay. Oh, Richard Chavan, I'm not able to see your screen. Is my screen visible? I noticed somebody just mentioned that my screen is not visible.
Visible, sir, visible.
Yes,
It's
sir,
visible.
visible.
Okay. Okay, thank you. Because somebody just sent me a note that screen not visible. All right. So this way you can see your predicted extension. So this little fella right there, these two line, what basically is doing is calculating my y. There's another way I can do the same thing. I can actually just if I want, I can just remove this and I can have my own custom function. I can just say my y, let's say my x or my extension. So I can say my predicted extension, predicted extension equal to, and I can use that little formula. Remember, this whole thing is a NumPy array, right? So my force is a NumPy array, and I can apply this formula. I can say that force. Okay, I can say A, which is what is my A and B, by the way. Let me just print out my A and B. Your A equal to coefficient COEFF, and read the value 0. This is my A. Okay, and my B is going to be equal to coefficient. This is how you read these values individually. Okay, this is my B, and then I print my A and B, A comma B, and I run this. Oh, coefficient. Oh, it's S over there. There's an S, and this should be 1. All right, there you go. So this is my A value, and this is my B value. So once I know my A value, I can just say A times force plus B. All right. Then run this. There's a lot of voice happening.
DC motor or AC motor.
Could you please mute yourself?
Continuous rotation with the applied signal, electrical voltage. Here, when I
Dr. S. Ram Prasad, could you please mute yourself?
system requires displacement at a particular angle. Those type of systems will require the stepper motor. Here, the stepper motor is going to give the output rotational displacement in stepwise, depending upon the number of pulses you are giving. Number of pulses you are giving.
Oh my God.
The number of angle movement. Number of angle movement. That depends upon the.
Can you please mute yourself?
And the rotor field. There are and the stator. Here the rotor.
S. Ram Prasad, please mute yourself.
State are having several poles, several winding, and rotor having permanent magnet with the rotor pin. For every one single pulse giving, there is a one incremental motion will be there. For the next
requested to admin please mute
I cannot even, I'm trying to mute him, but I cannot even mute him.
No, I said no, sir, not from you. I think admin can mute also.
Yeah, I don't know where is admin. I think he's probably sleeping somewhere, and he should be. Yeah, there. Okay, now it's muted. All right. Well, we just have to live with it. Okay. So predicted extension is A times force plus B. All right. And now I run this, and there you go. So see what I just did? I used my A value, which is this right here, and I use my B value, okay, and I apply this formula right there, okay, and this is my predicted extension. Based on this formula right here, this is the predicted extension. Okay, so that's what I did, and ran this, and there you go. You see, so these are my actual points, and this is the line which is this right here. Okay, this is the actual line.
Okay.
So this is my A, okay. So predicted extension. So there are more than one ways you can actually solve these problems. That's not the only way, by the way. Just thought you should know. So you can actually, like when I was doing these things, there's no such thing as this is the only way. You can actually arrive with the same answer in multiple ways. So I read my A and B. Okay, this is my A and B, and then after that, I now let's plot the above. So plot the above by using this formula. Okay, and there you go. All right, and then I put my labels. Okay, you can put your labels. Come over here, and now you can add your labels. Okay, to make it just prettify. I'm just prettifying this picture, and there you go. So now it's saying your data points is these ones. These are my data points. My fitted line is this. Okay, this is what my graph is. But this is my force right there. This is my extension. Okay. All right. So this is an example of your Hooke's law, where basically you are predicting or you're trying to deduce the Hooke's law from the data that's given to you. This simple example can be translated to any type of data. It doesn't have to be just Hooke's law. It can be like any data that you have, and you're trying to verify that. So you can actually transfer this concept to those little higher ones. Okay. Now comes we got okay, curve non-linear. So right now we were dealing with linear fits, right? But reality is in life, you're not going to come across simple curves. It's going to be non-linear. And the idea is simple. It's basically the same concept. There's not much to it. So non-linear curves, non-linear curve. All right, let me turn this into markdown language and look at my spelling of curve. It should be CU. All right, non-linear curve. So let me just save this thing. Non-linear curve. So let's say you have, where is that? Yeah. So in fluid mechanics, you have pressure drop through a pipe, and there is a relation, and this is the relation. This is something we know, that the change in pressure is equal to K times Q square. So the pressure drop is related to the flow rate. Q is your flow rate. So your change in pressure is equal to K times Q squared. This is something we know from our, people have done experiment. Okay, and we want to see something like this. We want to see if that's true. So by the way, let's try to understand what this formula tells us. This is a pressure drop in Pascal. This is a volumetric flow rate in meters cubed per second. And K is the flow resistance. Okay, this depends on your pipe diameter, your length of your pipe, your fluid properties, and so on and so forth. Suppose an engineer, let's say this is a data, suppose an engineer measures the pressure drop at different flow rates. So he's able to measure all this, okay? So the pressure drop, let's say is 15, flow rate is 0.1. When the flow rate is 0.2, the pressure drop is 60. When this is the flow rate, this is the pressure drop. And these are all his readings, okay? So the goal is this. that you have to find this type of relationship, del P equal to AQ square plus BQ plus C. Now, according to our law, right here, okay, there is no Q term and there is no constant. In other words, our B and C terms should be almost zero. They should be zero, right? So based on this reading right here, when we do this reading, and when we actually try to make predict our A, B, C based on this reading, our B and C should be zero. And let's see if it is. So in an ideal scenario, for turbulent flow and smooth pipe, your B should always be zero and your C should always be zero. Same thing as we did before, okay? In my curvilinear, remember, that's what we did. We actually tried to find our, where is it? Right there, your B term, okay? And I showed you your B term that came out to be is 0.03, which is a very negligible term. This term is very negligible. So when you start putting your F value over there, you're gonna see your B term, your B term is very negligible. And actually you can see that too, by the way. You can come back over here just to play around. You remember this B term right there. You can remove this B term, okay? Oh, you know what you can do? You can actually plot this curve. You can plot another curve, okay? So I can say predicted extension, and let's call this thing a predicted extension without B. Okay, let's say no B. Okay, so there is no B term over here. So you can see the difference between those terms, okay? And now I'm gonna plot all three of them. Control C, just to see what's happening. Predicted extension, no B. And I'm gonna make this color instead of blue. I don't want to make it blue. Let's make it magenta, maybe. Let's say I'm a magenta. I feel like magenta today. All right. So let's draw this. And where is my? Oh, look at that! It disappeared. Ah, there it is. So see, I'm actually plotting my predicted extension with my B term, and then without my B term. You see, I remove the B term. And after I remove the B term, look at my term. It's almost identical. You see that? So B, that's what I'm saying, your B term is very negligible. It's not creating much effect. So that's why we can safely say that our Hooke's law is holding. All right. So extension. Let's come over here. Let me just copy and paste this. Oh, where was that? Okay. And let me just copy this. Okay. Now we're doing the same thing. Now we're doing quadratic equation. Okay. We have basically, instead of dealing with linear equation, we're dealing quadratic equation. We're just doing it at a bigger scale now. So in this case, ideally, if this equation is to be true, this equation is to be true, that means our B and C should be zero. And let's see if that turns out to be true. So I have this data, my Q values is right here. These are my Q data values. Okay, this is my Q values and this is my P value. So I wrote my Q values, okay, and I wrote my P values. Again, in realistic scenario, you will get this data in a CSV file. And I showed you before how to read a CSV file. You can just read a CSV file right there. Okay, you can read a CSV file. You can take these columns. You can convert these columns into NumPy array like this. Okay, I convert it to NumPy array. Then you can do all types of calculation, and then you can do whatever you want to do with the calculation. That's what I'm doing over here. So I'm taking this data right here. Let me copy. Come over here. Untitled. All right. So this is my Q and this is my delta P. And then I'm calculating my coefficient. That's the first thing I'm doing. Okay. And after I calculate my coefficient, I want to print out those coefficients. Let me comment this line out. So I'm just running this code from here to here. I'm calculating my Q value there, my delta P there. I find my coefficient using polyfit. This is the same polyfit that I used over here, right there. Same function. Okay. And I'm specifying Q delta P comma 2, degree 2 right there. Okay. All right. Quality coefficient. And in this case, you're going to see 3 coefficient, because remember I'm specifying 2. Since I'm specifying 2, that means my coefficient is going to be something like this. Is a equal to ax squared plus bx plus c. So see these 3 numbers, a, b, c. That's what it is. So it's going to produce these 3 numbers. So those 3 numbers I'm reading, quadratic coefficient, it's going to be in this form. So I'm reading my A, reading my B, reading my C. So my A, I'm saying my A equal to, actually, let me just make it a little better. A equal to this, B equal to this. All right. All right. My A is equal to this. And my B is going to be equal to coefficient 1. I'm basically unpacking. This is called unpacking in Python. So I have my list. This coefficient is basically a tuple, or it's a list of a list. So I'm reading the first element, okay, which is A, reading the next element, which is B, reading the third element, which is C. And then after that, I'm printing my A, B, C. Okay, so I can say this is my A, this is my A, and then I'm printing my B, B, and then I'm printing my C, C. All right, let's run this, and there you go. So A equal to this, B equal to this, C equal to that. And you can see, look at my A value, 1,328. This is 110, small number, minus 11, small number. So B and C are small numbers. But remember, B and C, they're going to get multiplied. Okay, they're going to get multiplied by, if you come back over here, you see, B and C, they're going to multiply by Q. So they're only going to become more smaller. On the other hand, A is going to get multiplied by Q square. So because of this Q square term, this term is going to dominate. And these 2 terms, they're not going to dominate. Okay. So I got this. Great. Right now my A, B, C. Now let's plot them. Okay. So we're going to do exactly the same thing what I just did a minute ago. So I'm going to form my predicted, what you call that, predicted, where was that? Predicted pressure. Let's call it predicted pressure. So come over here, and so they're using something called fit function. You can use that too, okay? Or you can use predicted function. So right here, it's creating a polynomial. All right, let's run this, and there you go. So these are your actual points, okay? And this is the one that's created by this function. Oh, where is that? By these function A, B, C. Now you can actually use NumPy to create these functions. You don't really need to know, you don't need to create like this. You can actually use your NumPy values. So let's do that using NumPy values. So qfit equal to this. So let me just comment this one out. Okay. And let me comment this one out too. And let me use over here, delta fit, delta p fit. I want to define my own. Okay. Equal to, what was the formula for delta, that formula? It was basically, if you remember, it was P equal to A Q square plus B times Q plus C. That was your formula, right? A Q square plus BQ. So I'm going to say my delta fit is equal to A times and Q square. Now my Q fit, okay? I'm basically generating some values for my Q fit, and it's, remember, square, by the way. So 2 all right, and then BQ plus B times Q fit, all right, plus C. So this should be my delta fit. All right. This thing is just basically predictification. Let me comment this out. The most important part is this right here. So I'm basically, what I'm doing right now, I'm checking. I know my ABC. Okay, this is my ABC. I calculate my ABC, and then I'm putting that in the equation, and I want to see if my delta P fit, how does it look like? And my curve. Oh, look at that. This is my curve right there, and this curve is closely following your points right there. Okay, so that is great. So my delta P fit is this. So make sure in your free time, just go through this code and just try to understand what's happening. Okay, this will give you a little better idea and a little deeper understanding of what's happening behind the scene. So I'm printing my quality coefficient right here, and then I'm basically doing this. So this is my 4 right there. Come over here, and there you go. All right. Okay. So this I calculated, and here A is 1500, B and C can be ignored because they're almost 0. So here your A term is very big, and then you have Q square term. So A times Q square, it becomes a very big term, and B times Q and plus C, these are very tiny terms. So they are not really creating any big, a measurement error. Actually, if you don't believe me, I would actually experiment. Come over here and draw another curve. In that curve, remove your B and C completely. Now remember, in this case, my B and your B and C terms is there, right? So let's do it without that. So again, delta P fit. Let's say no B and no B and C. Okay, no B and C. In this case, there is no B and C. Equal to, and just copy and paste this one. There you go, copy and paste it. All right, and then let's plot that one too. So I'm going to plot this over here. I'm going to say this thing delta P fit, this one, right? No B and C. Right, and let's change the color. This is red, this is blue. Let's make it, can anybody think of a color? Cyan maybe? Cyan. And the label, let's call it quadratic fit, no B, C. C, all right. And let's run this. Sorry. And look at that. So this is the term, okay? This curve right here does not contain B and C term, okay? This one contains B and C. So you can see when you remove B and C, your curve is almost same. You see that it's very close to it, So experimentally, you can say that it is following very closely to that law, whichever that law was. What was it called? Let me see. It was called pipe fitting, pipe flow example. This was a pipe flow. So basically, this tells you a linear quadratic relation between pressure drop and flow rate. And so you can see that it is very quadratic in nature. You see that they're almost close to each other. All right. So copy this. Come over here. And there you go. Okay, so this is your curve fit for non-linear. Now, most of you guys come from a technical background, so I'm sure you guys experiment and you believe in experimenting. So experiment with this code, play around, try to understand what's happening over here. Basically, I'm doing delta P fit with all my B and C terms. Okay, then I'm doing without my B and C terms. That's what I did over here. So you see, first I did my B and C terms over here, right? This is my B and C terms right there. Then I'm doing without my B and C terms. And you can see the graph matches very closely with each other. So this way you can say that, hey, I'm happy with this law. This law is basically holding, it's holding its ground based on the data that you have, All right, now NumPy implementation. Let's do some implementation now. So NumPy gives you the ability to do all these formulas, right? Calculate the mean value, calculate the variance, standard deviation, and your square root and all those things. So NumPy has that ability. So let me just copy and come over here. All right, implementation. Let's call this thing as implementation. And let me change this to the Markdown language. All right. So I'm importing my NumPy. This is my value. Let's say I just made up this value. Okay, vibration. Let's say these are vibration millimeters, 2.3, 2.5, so on and so forth. Again, you can read this from a CSV file directly. All right. So let's say you read this from the CSV file and that's your data. How do you calculate mean? You say mean equal to np.mean. Great. How do you calculate variance? Well, your variance, if you remember from your statistics class, if some of you took statistics, variance formula is this. Basically, you say, let's say you have values x1, x2, x3. These are your values. How do you calculate variance? First, you calculate your mean value, right? You calculate your mean value. You got that. Then the way you calculate variance, you say x1 minus x bar, right? And then you square this term. Okay. And then after that, you divide it by how many data you have? 4 or 3, right? So you divide by 3. Okay. Plus, then you do the same thing. x2 minus x mean, square that, and then divide by 3 again, because the total number of data is 3, plus x3 minus x bar, which is your x mean, square the term, and divide by 3. All right. And then this is how you do calculation. This is exactly what's happening over here, right here. So I'm saying np.sum, sum basically would be adding all these terms. And I'm saying data minus mean. Data means these values. Okay. So from these values, subtract your mean. All right. And then square, you basically raise to the power 2, right there. And then you divide it by length. Because if you think about it, this whole thing, right? This whole thing is dividing by 3. So you really don't need all these 3. Okay. You just need 1 3 right there. Just one single 3. So I'm dividing by 3. Okay. That's what I'm doing. Okay. Now, how do you calculate standard deviation? So this is your variance, by the way. This is your variance. So this is how you calculate your variance. Now, how do you calculate your standard deviation? Variance generally, by the way, is written as a sigma square in mathematics. Some of you might have seen it. Standard deviation is written as sigma, and that is nothing but a square root of variance. Okay, so I'm just doing NP square root variance. So it's going to do square root of the variance, and that's going to calculate your standard deviation. This is a little tricky, this part right here. This is easy. Mean is easy because you just call it np.mean. It's going to calculate your mean. This part is a little tricky because NumPy, it does things a little bit different. Remember, there's because of NumPy, you're not using any more for loops. So NumPy is doing it for you. And this is one of the advantage of using NumPy library, that when you have a series like this, a series of data, you can actually perform these types of calculation a lot faster. So I'm saying data minus mean raised to the power 2 divided by length of the data. That's going to calculate my variance. And then I print my mean, variance, standard deviation. I'm using comma over here just to spice things up a little bit. I was using F before. Now I'm just using comma. Okay. Now let's run this. And when you run this, there you go. Mean, variance, standard deviation. It calculates that. All right. So not a big deal. We've done this. Now let's say you want to go one step further. Remember how we were calculating that value M and C from the cantilever right here? Oh, where is that? Nope, not this one. Right there. Right here. You see, based on this data and this data, your X and Y, you calculated A and B, your coefficient. A and B. This is basically nothing but Y X equal to mx plus c, right? Y equal to mx plus c. Exactly, that's what it is. This is in that form. Except I'm using different variable. I'm using x and f over here. So x is equal to 0.5 times f. plus 0.03. How do you calculate this number 0.03, 0.5 from here? What type of mathematical wizardry is going over here? And I'm sure most of you must be wondering, and I hope most of you must be curious to know what's happening over there, like how exactly it's done. So there's something called least square linear regression. They actually use this technique, and using this technique, they are able to figure out that value of M and C. So this is the formula. Now, since this is not a math class, I cannot explain you how this formula came about. So you just have to take it on faith that this is the formula that is used by a mathematician, that when you have the X and Y value given to you, you can find the M and you can find the C. That means when you have series of X value given to you and series of Y value given to you, like X and Y is your data given to you, then you can find your M and C using this formula. All right. So what I'm going to do, I'm going to just use this formula actually, I'm going to implement a function called linear regression that's going to take all these X and Y, and it's going to employ that formula and apply this formula over here. Okay, it's going to find your M, it's going to find your C. So just to give you a little quick rundown, what's happening over here is this. So let's say you have X1, let's say your values are X1, Y1, right? X1, Y1, this is your one data. Another data, let's say, is X2, Y2. And let's say another data is X3, Y3. Okay, so you have like series of data. I'm just, for simplistic case, I'm just taking 3 values. So your M is going to be equal to, according to this formula right here, is going to be equal to N. Now, what is your N in this case? 3, because there are 3 points. You're going to say 3 multiply summation of X times Y. Basically, what it's saying that you are gonna multiply these 2 values together. Okay, so you multiply X1, Y1, right? So actually, let me just put like this: X1, Y1 plus, then you do X2, Y2 plus, then you do X3, Y3. All right, and then it says minus, and then it's saying summation of X times summation of Y. So then it's saying summation of X would be X1 plus X2 plus X3 times summation of Y would be Y1 plus Y2 plus Y3. All right, so this is my numerator. Denominator is going to be N, which is 3, all right, times summation of X squared, meaning X1 square plus X2 square plus X square. Okay, and then minus summation of X whole square. In this case, it's saying that you say X1 plus X2 plus X3 whole square. Okay, and this, so you solve this equation right here. Solve this equation. Substitute X1, Y1 in this value. Let's say the values is 1, 2, 3, 4, 5, 2. These are your values. You substitute 1, 2, 3, 4, 5, 2 in this case, and you will come up with the value of M. Okay. Likewise, you can calculate your value of C. All right. So this was done in the back in the day, like when they didn't have computers. This is how they used to do. Now they have computers, so their computers can actually solve this equation a lot faster for you. And so let's do that. Okay. So I have my linear regression. It's taking my X value, it's taking my Y values. All right. So what it's doing, first is calculating the length of X value. Like how many X values do we have, right? So you calculate your length. Then you add all the X values. Remember at one point we added all the X values right here. You see the summation of X, this one. So that means we have to add all the values. So I do all my values, add all the X values, also add all the Y values, np.sum Y values. Why? Because of this term right here. Okay, we have to add all the values. Okay, next step. Then I'm multiplying my X value times Y value, right? And then I'm adding them all together. Because right there, you see this term right there, summation XY, right there. This we need to do this. So you can do that in NumPy very easily. You say np.sum X value times Y value. So basically I'm saying summation XY. And then there is a summation of X squared, which is right here, this term, this right here. So how do you do that? You say x value to raise to the power 2, and then you apply sum function. That's going to give you sum x squared. All right, I got everything now. And what I'm going to do, I'm going to substitute in that formula. This is my formula right here. This formula is saying basically this right here. So this formula is saying like this. This is what it's saying that actually not saying, but this is what it's stating, that m equal to n times summation xy. Okay, summation xy minus some x times some y minus summation of x times summation of y, okay, and then divided by n summation of x square, okay, that means summation of x square minus summation of x whole square, meaning this and then square. Okay, so that's what this is doing right here. All right, this thing is calculated right here. Okay, this thing calculated over here. Okay, this thing, summation of y, is calculated right there, and likewise you have summation of x right there, okay, which is this right there. All right, so I do this thing, this will give me my m, and then likewise there's a formula for c. I found my c. So m and c I found, return mc, and there you go. Okay. So so I found my MC and I solved it. So this is my X data right there. This is all my Y data, and I've put it inside my function. Okay, and it returns my M and C. And then I say my slope is let me just say 0.2e. Okay, slope is equal to this, and my intercept equal to this. Okay, let me just comment this line out. Okay, let me run this, and there you go. Slope is this, and intercept is this. Look at my slope. Is 2 times e to the power, 10 to the power 5. And my intercept is 2. Okay, so this is my linear regression. So this is, where was I? Right here. So this is me, the relation between y and x, and it gave me my m value, it gave me my c value. Okay, I got my m and I got my c. What is my m? Slope is this, and my c is this. So I just implemented a formula that actually calculates your M and C. Before that, what we were doing, if you go back on the top, you remember how we actually found M and C? We just found M and C using this right here, right there. You see this? This function did it for us before. But some of you must be wondering what's happening behind the scene. How is it calculating? Well, this thing is actually behind the scene. If you go back to the Python code, you're going to see this function running in the background. Okay, this is what actually ran in the background. You just don't see it, but they have, the creators of Python or NumPy, they have done it for you. So you don't have to redesign the wheel. You as an engineer can focus on implementation. Sorry, focus on the problem of using the function, not worried about how the function is being implemented. But I just showed you in case some of you are wondering. This is what's happening behind the scene. Okay, next topic. So this is done. Okay, cantilever, NumPy. All right, okay. Now comes, you can also implement the same thing in Python. So this is something I want to show you now. Same thing, implementing in Python. Not an easy task now. So somebody was asking me that at the beginning of the class, why do we use NumPy? And this is your reason. I try to implement this in Python, and look what's happening. First time, this is my data in a list. Okay, there is no numpy over here. N equal to len data. Then I calculate my mean. How do I calculate my mean? My mean is equal to sum of data divided by n. In my numpy, my mean was very simple. It was, where was my mean? Right there. You see that? Mean was np.mean data. That's all. But in Python, you have to actually do like this. All right. Then I have to calculate my variance. Define a function. Okay. This is how my variance was calculated. Okay. Now let's see how numpy did variance. Oh, look at that. Variance was right there. Okay. Or I could have done a formula. By the way, there's a formula called np.variance. That's another formula in your, let me just show you, or I can just say, or variance equal to np dot var. Okay. Then specify your data. This is another way. You see, I can calculate my variance like this. All right. So I got my variance. Then I calculate my standard deviation. Standard deviation, how do we do? Remember, there's no square. I'm actually using something to the power 0.5, okay? Because that's what just square root means. And then I calculate my mean variance standard deviation. This is how I came across my mean standard deviation. Now, I got to calculate least square linear regression equation, meaning I have to find M and C, not using NumPy, but using pure Python. And this is what I'm doing. You see that? So the code is a little bit different now. Okay. And now, where is that? The linear regression XY. So in this case, there you go. You see, I'm using this functionality called zip over here. So if you look at this code, it's pretty much same as this. Okay. The only difference is this one gives you, NumPy gives you some additional functionalities, and it's a lot faster. NumPy is specifically designed for these like numerical computations. Okay. So this is the Python way, in case if you're interested. Okay, then there is that. Okay, so this is your NumPy application. Now let's go to next topic. Let's do an implementation. Sorry. There you go. Okay, SciPy application now. So we did NumPy application. Okay, now we gotta do SciPy application. So SciPy is a short for scientific Python. So it basically allows you to do these perform some of the common operation that's needed by engineers, scientists, and engineers and mathematicians a lot. So SciPy is a pretty cool tool, and if I were you, I'll actually get familiar with SciPy if you use a lot of numerical computation in your engineering field. So let's say you want to integrate. So SciPy actually has a function called integrate, and that allows you to do integration. So let's say you want to integrate this function. Let me just copy, come over here, and integrate. This is integrate. Let me open up another cell. Okay, so let's integrate this function, fx equal to x squared. Okay, and I'm sure you guys have studied this function, everybody at some point in their life, everybody, at least all the engineers. When you integrate function like this, you use a piece of paper. And let's say you want to integrate from 0 to 2. So if you do it on a piece of paper, let me just show you. Okay, so integrate x squared, right? Dx from 0 to 2. That's what you're trying to accomplish. You're trying to integrate this. So this is my fx and my 0 to 2. So the way you do is first you specify your function. Okay, what exactly your function you're trying to integrate. Okay, so this is my function that I'm trying to integrate. This is my fx. Okay, so my f, the way you specify a function, this is one way. There are other ways too, but the one I use is actually lambda expression. I say lambda x colon x to the power 2. So this is my function x to the power 2. Okay, this is my function f. And then I call this function called integrate. Integrate.quad, and you give your function f into it, And then you specify your A value, specify your B value, specify your 0, specify your 2. So in either case, you need 3 things to specify to integrate. You need 3 things, right? To when you integrate something, you need your initial value, where you're starting from, 0, where you're going to, 2, and the function f, which is this right there, f. And what is this f defined? I define it over here. I'm saying f equal to lambda x colon x squared, okay? And then I integrate this. So when you integrate the SciPy, it will give you the result, and also it will give you the error. So it gives you both information. So you can print both your result and error. So if I run this now, so when I run this, and there you go. Result is 2.667, and estimate error is 2.9 to the power 10 to the power minus 14. So this is your error, and this is your result. Okay, where is my result? Yeah. All right. Now let's go one step further then. Let's do some application of this. Let's say you have a car. This is the car, and it's moving on a road. And we all know the formula for distance traveled by the car. It's basically integration of velocity over time times dt from 0 to t. But vt is, let's say, given to you in speed in kilometers per hour. And t is the total time. So in real world, how do you calculate the distance traveled by a car? But in real world, you would not be given this vt. This would not be given to you, because vt, remember, as you drive your car on a road, you don't know what your vt is, because your velocity at every time is changing, right? There's no, like, you don't know your function. Maybe I misspoke. What I should be saying is that you really don't know your function, the true function, how exactly it's looking like. So let's say you go from Gurgaon to maybe, let's say, Kerala, and takes you, like, let's say, maybe 3 days to go there. But if I ask you to write me your function vt, there's no way you can write function vt. So since you cannot write function vt, you cannot do this computation. You cannot do this integration. So then how would you calculate this function? Like, how would you do this thing? Well, what you have is the next best thing is the data. You have data from the sensors. And let's say, let me just copy this. Come over here. So let's say you are going, let's take a small case. Let's say you're traveling your car, took you 20 minutes, and you have a sensor, and that sensor records your speed at that time. That's it. It measures your speed at that time, and it tells you every minute what is the value. So I'm creating my time minutes in np.arrange 0 to 21. Basically, I'm just creating these values, and this is my converting into hours, and this is my data. So at 0 time, the speed was 0. Then later on, 1 minute later, the speed is 20. 2 minutes later, speed is 40. 3 minutes later, 50. 4 minutes later, on the 4th minute, 55. On the 6th minute, 60, 62, 63, 64, 60, 58, 55, 52, and so on and so forth. There are total 20 readings for 20 minutes. Okay, there are 20 minutes reading, and each reading is done in 1 minute. So this is your typical data. Now, convert into array. This is your time. So if you plot it, it's going to look something like this. Okay. So come over here, and I plot this thing. I plot my time series and everything. And I don't want rest of stuff. Let's say rest of thing I do not want to see. Okay, so let's comment everything out. And okay, let's run this. And there you go. You see, this is your data right here. So this is your speed curve. Speed and data. Oh, I heard AV Panindra saying I'm not audible. Is my voice audible? Can I get some confirmation, please?
Hello?
Yeah, it's
you're
audible, sir.
It's audible.
I'm audible? Okay, thank you. So yeah, if I'm audible to most of you guys, and some of you are saying I'm not audible, maybe it could be on your side. Maybe you can check on your
It is
speaker.
audible, plus you are explaining very well, sir. Good.
Thank you, Ranjit. I appreciate that. Thank you. You're a good student too, man. Thank you. All right. So now let's say you have this. Where was I? Right there. Okay, so let's say this is the data. This is the data that you collected from a sensor. All right. This is your data. Now remember, look at this curve. Clearly, you cannot plot. You cannot write a mathematical equation for a curve like this. That's a weird looking curve. So plotted this, okay, using plot library, time minutes, speed kilometers. So this is my x-axis in my time, and this is my y-axis. And you know what? I want to put some labels because see, there is no labels over here. So let's put some labels over here. So how do I put some label? Well, if you guess, there's a command called x label and y label, and you would be right. Time and speed. Title, vehicle time, vehicle speed versus time. So that's my title. So it's going to create an X label, it's going to create a Y label, and it's going to put a title over here. So let's run this, and there you go. Vehicle speed versus time. This is my time, and this is my speed. And I'm also putting some grids over here. You see, grid equal to true. Okay. Now I want to calculate the distance traveled. Now, if you remember from your high school man, or not sorry, high school man, but from your 11th and 12th class grade, how do you calculate distance traveled by a vehicle? You actually integrate, right? Yeah, you integrate the curve, right? You integrate this curve and you basically calculate the area. That's what you do. You calculate the area. So there is a function called, there's a trapezoidal rule. And oh, sorry, where was I? I went to a wrong place, did I? No, yeah, right place. Okay, so what I'm going to do, I have to calculate the area, right? So you can actually calculate the area solved by calling this function. In NP, there is a function called trapz. Okay, and in that case, you just have to specify this function speed underscore your x-axis, okay, which is your y-axis over here and your x-axis over here. So your y-axis and your x-axis, you specify that, and that's going to give you the area in between that. Okay, so let's do that. And there you go. My area is 13.98. So the distance it travels is 13.98 kilometers. Okay, so I'm just writing my whole, it calculates the distance for me. And I'm calculating distance trapezoid, and I'm writing my value over here. I'm just using the F string. Okay, calculate that for you. Now there's another rule called Simpson rule. I can do that one too. So let's employ Simpson rule. All right, and this is your y value, this is your x value. And let's see if it gives you the same answer. And look at that, it does. 13.98, 14.02. Now the reason there is a little bit of error, tiny error, is because the way the trapezoidal and Simpson rule works, they work a little bit different. The triangles, one actually takes over the curve, the other one takes the height of the triangle under the curve. So that's the only difference. This one, Simpson, takes over the curve. That's why you get extra value. This one takes under the curve. That's why it takes a little bit less value. Okay, so this is your Simpson rule, and I applied that. It gave me the distance traveled. So in this case, I was able to figure out how much distance a car traveled based on the speed. That's all I knew. Based on the speed collected every minute for the next 20 minutes. This is how it's done in real life. All right. Where was I? There was something. Okay, yeah, let's come over here. All right, plot this. Plot this. Okay. Now, another application of integration. Total volume. Let's say you're a plumber. You change your profession. You got tired of engineering. You say, you know what? I want to downskill myself or upskill yourself, depending on how you look at it. And you become a plumber. And your job now is to calculate the flow rate. Your job is to calculate the total amount of volume of water that passes through a pipe. And what's given to you is the flow rate, QT. QT is basically flow rate. So depending on the flow rate, you have to calculate what is the total amount of volume of water that passes through this plumbing or through this pipeline. All right. And by the way, the flow rates, they can be measured through sensory data. Meaning you have these sensors, you can put them inside these pipes. They are like giant pipes. And these sensors will record what is the flow, of the water that's passing through those through that point. So I'm simulating that data right now. I'm creating 0 to 10 hours. Okay. This one, by the way, A dot range, you're going to see this time and time again. This is pretty handy tool, A dot range. What it does, it allows you to create your values. So if you come over here, let me just come over here actually real quick. Let me copy and paste this code and show you. All right. So NP arrange is basically a function that allows you to calculate, that basically gives you the ability to create a numbers on the fly. So if you want to create 0 to 20 numbers, you can just say np.arange, and that's going to create 20 numbers. One way to create 20 numbers would be you would have to write time. Let's say if I ask you to create me 20 numbers, okay, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 21 or 20. How would you do that? Well, you're going to do like this, right? Some of you who are not programmers, you will think that I'm going to write np.array, and then over here, go over here, type 0, type 1, type 2, type 3, type 4, and then you get lazy. You say, oh my God, that's too much to do. So is there a shorter way? And the answer is yes, there is. And this is the command, np.arange 0 to 21. It's going to create 0 to 20 numbers for you. And if you don't believe me, which you should not, just print it out. Print your time minutes. Time minutes. All right. And let me comment out everything, by the way. So this way, all right, comment everything out. So I create 20 numbers from 0 to 20. Run this, and there you go. 0, 1, 2, 3, 4, 5, 6, all the way to 20. All right, created that. Now I'm going to convert that. Remember, this is in minutes. I'm going to convert this into hours. All right. Oops, sorry. Oh. All right. Converting to hours. If you want, you can print it out. Okay. Time hours. Control C, Control V, and run this. And there you go, hours. Now it's converted into hours. Now look, it's basically, it's a very big number, right? It's 0.0067. You can round it off if you want, if you feel like, but I'm not rounding it off, I'm just leaving like this. Okay, so I convert the numbers, round it off. Let me just comment this line out now. Okay. Then I have my speed function. Now, let's say, oh, sorry. Let me just come down a little bit. All right. So we know your speed. Okay, let's say the speed is given by this equation. Okay, speed is equal to 3 times time to the power 2 plus t. So this so your speed, your velocity, okay, is given by 3 times t square plus t. Right? This is a, let's say, equation of a okay. Oh, hold on. What just happened over here? Oh, I'm sorry. This is what was I teaching? Oh, I went to the, oh, this is what I was supposed to be doing. I apologize. I was supposed to be talking about this. I was thinking there's something I already covered. Okay, total volume. We were talking about the total volume. Oh, my apologies. Went to the wrong topic for a second. Come back over here. So, all right, there you go. So I create those arranged from 0 to 10 hours, okay? And then I convert into seconds. So how do you convert hours into seconds? You multiply by 3,600. It did that. And I showed you a minute ago, like how you can print those values, printed those. This is what the Q. Now let's say this is my Q value. Okay, this is what was measured. Okay, you actually had a sensor on the pipes, and right here you had a sensor, and the sensor measured all these values for you. Okay, and then let's plot that. Okay, let's plot those values, and that's all we do. We just plot that. Plot it, and we're not going to do any computation. We plot it. So I'm going to plot your time and time in, let's say, hours, and Q, which is this value, and marker is this right there. And there you go. So see, it plotted all these values. So as now I want to do some X and Y, right? I want to see my X and Y values too. So I can just uncomment this thing out. So this will give you more description. All right, flow rate and time hours. So as the time is going in hours, let's say it's from like this, your flow is goes up, goes up, goes up, goes up, then it comes down. Now, remember, this is a plot, by the way. This should be actually a scatter plot. So scatter, basically what it does is plus the point. So if you come over here, it's going to plot just the point like that. Okay. So that's the difference between your scatter plot and your regular plot. So let me copy, paste it. And depending on whether you like scatter plot or regular plot, you can do either one of them. That's up to you. Oh dear God, what happened? That was weird. Okay. It was plot. Plot. All right. Okay, so you can either draw, you can either use scatter or you can do plot. That's up to you. So I'm using plot now, and this is my plot right here. So let me copy and paste this part. Over here. Okay. Now I'm going to apply the trapezoidal rule. Same thing that I was doing before. And in my trapezoidal rule, I'm supplying my Q values. Basically, I'm supplying these points. Okay, I'm supplying all these points, which are measured through a sensor. I supplied that, and I'm supplying my time, which is my x-axis, which is right here. I'm supplying my x-axis value through time seconds. And then this trapezoid, this function trap, is going to calculate the area for me. Or in other words, it's going to calculate the integration for me. And that integration would be my volume. Run this, and there you go. So according to the trapezoidal rule, my answer is 424. But if you use Simpson rule, the answer is 427. So without actually knowing the function, okay, I did not really I did not really had access to the function. All I knew was the general form of my function is something like this. And I knew through my data what my Q values are. So based on my Q values and the general form of my function, I'm able to determine how much volume of the water has passed through this pipe. Okay, next topic, battery discharge. So let's say you now have been hired by NVIDIA, and they're making some type of super battery, so like a great battery, and they want to determine how much energy is delivered by the batteries. Now, if you remember from your engineering class, your power is voltage times current, right? Because higher voltage means you lose more power. Likewise, higher current means you lose more power. So voltage is basically, power is basically voltage time current. So the total energy that the battery discharge, the total energy battery loses or gives out, is basically integral of that power with respect to time. Okay, so this is the formula. All right. So let's do the same thing. Now, what you can measure, you cannot measure energy directly, right? What you can measure your voltage and you can measure your current. So if you have a battery, let me see if I can draw a picture of a battery. Yeah. So if you have a battery, okay, with two points like this, so you can measure a voltage. I believe it's a voltmeter, and you can measure current using ampere. I think that's the. I think this is how you measure. I don't know. Okay, so you can measure your voltage and you can measure your current. In other words, you can measure your V and you can measure your I. So by measuring your V and I, you can determine your E. But here's the thing. To determine your E, you need to integrate. So let's do that now. Okay, so I'm just saying my time in minutes. Basically, again, I'm calling that function. I'm basically creating 0 to 60 minutes every 5 minutes. I'm creating a numbers like 0, 5, 10, 15, 20, 25, and so on and so forth. So this is the way I'm creating. So I'm saying create me numbers from 0 to 65, step size 5. Yes, this 5 means step size, okay? And time hours is basically you divide this by 60, that's going to convert into hours. And then time in seconds. And then you take your time in minutes and multiply by 60. So this is going to give you time in hours and time in seconds. So I'm basically having these values. I'm actually creating all these values in different time units, okay? I'm creating my time in minutes and hours and seconds. Why are we doing this thing? You will find out in a minute. These are my voltage readings, okay, over time. So at one time I measured my voltage at 4.2. Another time I measured my voltage at 4.15. By the way, when I measured my voltage was 4.2, what was my current? 2.0 at the same time. When my voltage was 4.15, my current was 1.95. So these are the corresponding values of these voltage, okay? All right, and how many are there total? Let's see, I would say 10 maybe? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 or 14, yeah. All right, so we got all these values. First thing is compute your power at each point. Now remember, to do your integration, you have to know your P, right? PT. And what is PT? Voltage times current. That's what I'm doing. I'm calculating my power is voltage times current, meaning this voltage multiplied by current. So it's going to take these numbers, 4.2 times 2, it's going to calculate the answer. 4.5 times 1.95, calculate a number, and same thing, it's going to multiply these corresponding numbers. All right, so I got my power now for each interval. And then after that, I plot my voltage with time, and I plot my, actually, let me just come over here, comment this one out. Oh, dear God, what happened over here? All right. Okay, then I'm specifying my figure size, and this is a subplot. Don't have to worry about it right now. This is the main part, okay, right here. And all right. Okay, so I'm plotting my voltage versus time, current versus time. I'm just plotting them. That's all I'm doing right now. Come over here, and where is it? Oh, it did not plot. Look at that, disappeared. Oh, there it is. So this is my voltage, okay, voltage, and this is my current right here. So voltage values, each one of these dots, they are values. If you want, you can actually have scatter plot. So you can remove the plot value and you can put scatter over there. That's going to give you a scatter plot. All right, I got this. Now, I want to plot my power and time. Okay, power and time. My X is time and my Y is power. Okay, so let's do that. And there you go. So you have, this is my voltage and current, and this side right here on this side is my power. So let's look at one of the values. Let's look at this one right here. At time equal to 0, what is my current? It's 2. And at time equal to 0, what is my voltage? 4.5, right? So 2 multiplied by 4.5, and the answer is approximately 9. So at time equal to 0, which is right here, my voltage is approximately 8.6. So it's basically, let's see, let me just be absolutely sure. 2 times, 4.2. So 2 times 4.2. So this is 4.2, not 4.5. So 2 times 4.2 is 8.4, something like that. I see that 8.4. All right, let's do one more. Let's do this one right here. When my time is 10 minutes, okay, what was my reading on my current? My reading is approximately 1.8, okay, 1.8, something like that. Or you can just go and check over here. 1.9. This is my current. And what was my voltage? 4.91. So 1.9 and 4.1. That was my reading. So what's going to be my voltage? What's going to be my power? It's going to be this multiply by this. Okay, and your answer would be, you can multiply 4.1 times 1.9. You can do on a calculator, and your answer will come out to be 10. It's going to be somewhere 7.8 maybe. 7.8, yeah, so the answer would be approximately 7.8. So this is how you came across 7.8. This is how these values are formed. Okay, so I got my power now. I got my PT right there. And now I have to calculate energy. What is the energy? It's the area, right? Area under the curve. If you remember from your high school, I keep saying high school, but from your 11th and 12th grade, the integral of a curve is nothing but the area under the curve. So the integral of this curve would be the area, right? So you can actually calculate the area right now just by looking at this. You can tell the area is going to be approximately, remember area of it, this is a triangle, right? Almost a shape of a triangle. You can do a rough calculation right here. Half times base times height. So your base is 60 and your height is 5 to maybe 5, let's see, 1, 2, 3. So 3. So 3 times 60 divided by 2, so 345. So approximately 45. Just kind of like a rough figure, okay? So let's see if that's what the answer comes out to be. All right. Oh, where was I? Yep. All right, let's run this. Let me uncomment this line out. And there you go. Oh, look at that. So it's using a different unit. Okay, because they're using different unit, the answer coming up is 6.66 kilowatt or 23,977.50 joules. So basically it's the area under this line. That's what it is. Now they're using a different unit. Okay, so based on the unit they're using, like over here they're using joules, over there using watts per hour. This is minutes. So you would have to convert that in the right unit, and you can just manually calculate your, if you want, you can visually calculate your area under the triangle, and that will give you same answer as this. So this is how they were able to find total energy delivered by this battery in how much time? It's from 0 to 60 minutes in 1 hour. Okay. Okay, so just based on the reading of your current and voltage, you are able to determine how much energy did the battery store or how much energy it gave out. All right. Okay, next topic. Now comes ordinary differential equations. So this is another application of your, what you call that? Yeah, of your Python. Okay, so using your NumPy and SciPy library, you can solve these ordinary differential equations. So let's say you have an equation like this: dy by dt equal to minus 2y, and initial condition is y at t equal to 0 equal to 1. If you remember your ordinary differential equations, the way you solve them, you specify your initial conditions too. In this case, it's a one variable, y, one independent variable, one dependent variable. And in the initial condition is that at t equal to 0, your value of y is equal to 1. So we know from our experience, like we have some of you who actually have done ordinary differential equation, you know that you can solve this thing easily. And when you solve it, the answer would be e to the power minus 2t. This is your analytical solution. Yes, sir. Somebody has a question? Okay, no question. So this is your analytical solution. Now, you want to solve it numerically. You want to calculate the answer using your, you can actually calculate this answer using numpy and, scipy inbuilt functions. And the function that is used is called solve_IVP. Okay, it's IVP basically stands for initial value problems. That's what IVP stands for. So solve initial value problems. So under integrate, you're going to see solve IVP. This is the method I'm going to be using. Okay, so let's do that. Let me copy this over here, paste it. So first thing first. Now remember, I'm trying to solve this equation. I'm going to try to solve this equation. So to solve this equation, first you have to define the equation. What is my dy by dt? You say def dy dt t comma y, and the answer is minus 2 multiplied by y. That's my dy by dt. So minus 2 multiplied by y right there. Okay, this is my dy dt. Okay, define my dy by dt. Then you specify your initial conditions. What's your initial condition? My initial condition is y at t equal to 0 equal to 1. So this is how you specify your initial condition. You actually put this inside a list. And the reason it's putting inside a list because in this case, your IVP, this solve IVP is a pretty powerful library. It not only solves one variable, it can have 2 variables, 3 variables, 4 variables. It can have many variables equation. Okay, it allows you to solve that. So because it has many variables, that's why you're using the list over here. Okay, in this case, I'm just saying this. It's a list of value. In this case, my initial value is just 1. All right. Okay. Oh, where was I? Now let's define our time span. Now you are trying to solve this. You have to specify like from what time to what time you're trying to do this. Okay. So I'm saying from 0 to 5. Number of points. Now how many points I want? In this case, let's say I want 40. You can play around and change this to maybe 6, 7, 10, 15, you know, whatever you want to. And then you apply the solve IVP. And this is the magic right here. This is the function that does everything for you right here. And then you can print out the solution. Let me just comment this whole thing out first and show you what's happening. Okay. Right here. Once I solve this thing, I come across this, right? This function doesn't mean much to me. What means to me is the number, the numerical value. I want to know what is the value of y at t equal to 0? What is the value of y at t equal to 1? What is the value of y at t equal to 2, t equal to 3? This is what I want to know. So those things are important to me. Before I continue, am I still audible?
Hello. Yeah, you're audible.
Yes, sir. Okay, thank you. I just want to make sure. Okay, where was I? Yeah. So to us, like engineers, like this function, if somebody gives you this function, you cannot really do anything with the function. You work with the numbers. So this function doesn't mean much to you, but the numbers mean to you much to you. So when you have this function, you convert this into a number, and numerical value is what you're working with. So come over here, and this one, I create my numerical value. I create my t values. My t values are basically from 0 to 5. All right. This one actually creates 0 to 5. And then I put this inside my solve IVP. And then I print my solution. So let me just run this code and show you the solution. And where is the solution? Okay, true. There you go. So done. Yeah. All right, solution T and with solution. There you go. So the solver successfully reached the end of integration interval. Success true, status time. So it prints out all the time and it prints out all the corresponding y values for each one of them. Okay. So these are my time values and the corresponding y values. All right, great. Now let's study this point right here. What exactly is happening over here? Because this is where all the magic is happening. So your solve IVP is an inbuilt method. Okay, it's an inbuilt method inside scip.integrate. Okay, I import that inbuilt method. And inside this, I'm specifying my function, which is this right here. I'm specifying my t-span. Okay, I'm specifying like how much t value do I want it to change from where to where. All right. Then I'm specifying my y0. What is my y0? Initial condition. You remember, to solve this problem, you need dy by dt. You need your initial condition, right? And then also you need series of t values. You need series of t values because you want to evaluate this. Remember, it's not going to give you this answer right away. It's going to give you the numerical value. You want to know the numerical value because that's what you care about. Okay, so then you specify your t values. So this is what my t values are, t evaluation. np.len space, which is short for linear space, 0 to 5. And how many points I want? I want, let's see, you know what, maybe I should have put this thing, t-span is 0 to 5. Yeah, I should have put this over here. Yeah. So 0 to 5 and number of points. So basically I want 40 points. Okay. My number of points is 40. So create 40 points between 0 and 5. That's what this is doing there for me. I could have written down this a little bit on the side over here just to show you, but I think I showed you before, so you can actually you can anytime when you have a doubt like what this function does, what I would do is just copy this thing right here and print it out. Come over here and print it out. Okay, don't be scared to print stuff out. The worst thing that can happen, you can crash your computer. That's the worst thing can happen. And if you work in a government, you should be good. But if you work in a private company, good luck with that. All right, you see that it printed all my values from 0 to 5 and it created 40 of them. Number of points is 40. So it created these 40 points for me from 0 to 5. That's what it does. All right, where was I? Lost. Oh, there you go. Okay, and then I print my solution. So this is my solution right here. Okay, this is what actually it returns when I run this. Okay, now remember this is the solution that this function printed, but we already know the answer, right? We can already calculate this. Remember this, from this we can calculate our answers, right? We can calculate y at t equal to 0, y t equal to 1, y equal to t equal to 2, t equal to 3. We can calculate all that. So let's do that way and also compare that with the value that is computed for us by this function solve IVP. So just to see that, hey, is it making sense? I know this is how it's supposed to be, the answer looks like, and I want to see that if it makes sense. So this is what I'm doing. I'm actually exact solution for comparison. So how do I calculate my exact values? I know my t exact is NP linear space. So this is my t exact. Okay. And actually, you know what? Yeah, t exact is this thing. And y exact is np dot exponential minus 2 to the power t exact. Okay. This is basically, this one is this right here. This right there. Yt equal to e to the power minus 2t. So np exponential minus 2 times t. That's what's happening. Okay. And then once I find my exact value, how do I know, how do I compare one against the other? Well, one way is I can print them out next to each other, right? So if I print them out next to each other, oh my God, that's going to take like, it's going to drive you crazy. So let me just show you. Actually, I've done this before. I try to print it out next to each other and it kind of like, did not give me result that I was looking forward to. What happened over here? All right, there you go. So say print. Okay. Print your, now how do you access the solution, by the way? Remember the solution was this right there. How do you access that? Well, you say solution.y0. This is how you access. You don't have to remember all these things. As I was saying, you just have to, if you ever forgot, just go to any one of the tools like AI tools and just ask it, and it's going to tell you that. So that's my solution that's predicted by the, not predicted, but by calculated by the function IVP, this one. Okay, so I'm printing solution dot y0, and then I'm also printing this right here, y exact. So this is the exact one, and I want to see them next to each other. And let's run this and look at that. So this is my the one that calculated, and this is my exact solution right here. Okay, this is the one that was calculated, and this is the exact solution. So just by looking at this thing, you can tell, oh my God, how am I going to do this? Is too much calculation. How am I compare this? Well, you can compare using a graphical tool. You can actually plot them next to each other, right? And I'm sure some of you must have thought of that, and you would be right. So what I'm doing, I'm plotting them now. I'm plotting my solution.t, which is my time axis, and solution.y0, which is my, this is the one that's the solution. I'm plotting that, and I'm also plotting my exact value next to each other. Okay, so this way I know how are they doing, like how are they comparing next to each other. When I plot them, and there you go, you see that. So this is my numerical solution, and this is my exact solution. So numerical solution, exact solution, same. There might be a little bit difference, but it's going to be very tiny. So I'm happy. I can see, but my numerical solution that solve IVP that produces matches with my exact solution. And I know my exact solution, right? In this case, exact solution was this. I already know because I've done it through with my hand. Okay, so once you're satisfied that, hey, you solve IPP works, now you can actually use it to calculate more complicated expressions, more complicated results. All right, let's see, where was I? Okay, now let's move on to the next application. Cooling of a hot object. Let's say you're a coffee drinker or tea drinker, whichever you feel like, or whichever is your taste of, choice. And we know the Newton law of cooling says this about the temperature. It says that the rate at which the temperature changes is equal to minus K times the current temperature minus the environment temperature. So this is the equation right here. Okay. So T is the temperature of the object, which is your coffee, and environment is the room temperature, and K is the cooling constant. It depends on the material, airflow, and so forth. All right. So this is the Newton law of cooling. That's what it says. Now let's say what's given to you is initial. Remember, your initial temperature has to be specified. So they give you the initial condition that at time equal to 0, your initial temperature is 90 degrees Celsius, meaning the coffee is 90 degrees Celsius hot. And what is the room temperature? Let's say it's 25 degrees Celsius. Okay, you're living in, like, let's say South India. It's nice and pleasant over there. It's 25 degrees Celsius. If you're living in Gurgaon, like I am, and maybe the temperature is, let's say, 41, 42, or if you're really unlucky, maybe in summertime it's 51, 52 degree. All right. So let's say it's 25 degree. Maybe you're living in a coastal area, 25 degree, nice and cool. And your K is equal to 0.1. Great. So we know these three parameters. We know the exact solution for this. We have done this on a piece of paper before, and this is the solution. Time, the temperature at any given time is equal to environment temperature plus this thing, e to the power minus kT. This is your value. So for our coffee example, which is if you plug in these values inside this, this is your exact value. Now let's see if we can solve this, if we can come up with the same expression using solve IVP. Okay, we're gonna do the same thing that we did, like same concept. We actually gonna use numerical solution. Then we're gonna do the exact solution. We already know the exact solution is, this is the exact solution. So we're gonna compare the numerical value with the exact value, and we're going to try to see how they are they matching. And you would not be surprised if they are matching, because that's why I'm teaching over here. That's why I'm over here. If this value would not have matched, it would have freaked me out. All right. So let's copy, come over here, paste it. Thanks to the creators of copy and paste again. Makes our life a little easier. Don't have to keep retyping the same thing all over again. Okay. So basically, if you look at this code, this is same as the one I just did right here. Okay. This is the same as this. Pretty much the same. All right. I'm defining, remember how I define my function, then I specify my initial condition, then I specify my initial points like time spent point, and then I use my solution solve IVP. So this is exactly what I'm doing over here. Parameters, define my equation dt by dt, right? Where is it? This one right here. This is my function, right? So this is my function right here. And then I'm specifying my time, t evaluation, np linear space, okay? You know what, maybe I should have done that one too. I should have written down this like that, right here. Now I kind of think about it as I was teaching, I kind of dawned on me that maybe I should have written down. Generally, it's a good idea to, when you don't want to put too much big numbers over here, that can be a little confusing. So t eval equal to this, okay? So now you can say t eval equal to t eval. T eval, all right. And let me just copy this, come over here and do the same thing. Paste, and then remove this. T eval. All right. So I got this. Then where was I? Keep losing. Where was I? Oh, there it is. Okay, so I got my t eval. Now basically I'm just using the same function, but it's the same thing what I just did a minute ago. Specifying my dt by dt, specify my t span, my t0, which is my initial condition, right? Where's my initial condition? T0. T0. Okay. Okay, T0 would be something that I would have to, let me see something, T span. Okay, so this, oh yeah, Y0. So initial condition right there, Y0. So T0 must be defined somewhere. Oh, there it is. T0 right there. Okay, this is my initial condition. So I'm specifying initial condition and my T-val, which is right here, okay? Okay, solve it. And then I'm also doing the exact solution. I already know my exact equation, what exactly my equation is. It's basically T A N V plus this thing plus this, such a long expression, which is right here. I already know my exact evaluation. My exact function is this right here. Okay. So I'm also calculating my exact values. I'm calculating my solution from my numerically, using this. So let's come over here, solution. All right. Okay. And then I'm plotting them. I'm plotting both of them together. So just like I did before, basically it's the same code as the one before that. Okay, just go back and look at the code and you'll see it's exactly the same. The only difference is I'm just using a different equation. All right, I'm calling the same function, solve IVP, same parameters is being passed. I'm supplying this, run this, and there you go. So you can see that your numerical value, okay, which is the blue dots, and then you have exact solution, which is the red line, and then you have room temperature, which is dot dot. So which makes sense. Oh, there you go. This is room temperature. You see that room temperature. So look, your numerical value and exact value, they're matching, right? And I'm actually using plot. If you want, you can use scatter. You can use scatter. Scatter. So the difference between plot and scatter is that plot will give you a line. It's going to connect those points with a line. Scatter is not going to connect that. It's going to just put the point as it is. And oh, look at that. Did I crash the machine? No, thank you. Oh, dear God, what happened over here? Okay, so scatter In this case, scatter did not work. Okay, maybe it's because some value over here, marker size, yeah, that could be a reason. So let me just go back to plot then. I mean, there's a way to do scatter, but if I do scatter right now, I'm going to end up wasting too much time. Don't want to be doing that. All right. So there you go. So this is my temperature. You see, as the coffee, this is my room temperature right here. This is my room temperature at the bottom, which is 25 degree. And I start with my coffee, which is hot, and my numerical value, which is from using my solve IVP, is my blue circles, and exact solution is the red ones. And you can see blue and red ones are coming down together. They're perfect match. And then you see it's coming down, coming down, coming down, and then it touches, it becomes asymptote to my 25 degrees Celsius line. Great. It matches. All right. Okay, so, oh dear God, it's almost 2 o'clock. All right, gentlemen. So, I mean, it's a big topic. And for me to actually explain every single thing, it's going to take a long time, a couple of weeks. But I think you got a gist of what you can do with Python, and good luck with your learnings. Okay. Okay. Any question up to here so far before I leave?
Hello. So, dear participants, if you have any query, you can directly unmute yourself and ask the expert, or else you can also let us know in the chat box section.
All right.
So
okay.
I have a question. How do you that remark part? How do you remove that remark all of at once?
How do I remove what?
Remark sign.
Remark. Oh, these comments right here.
Yes.
Oh, these are called comments. Okay.
Yes, sir. Comments.
So what you can do is there's a control key, and then hit control key, and there's a /. So if let's say if I select this, right? Let's say I select this, and then hit control key and hit /, and that's gonna comment the line out.
Okay,
and if you want to reverse the effect of that, you can do the same thing again, and it's gonna reverse it. Okay.
Control and forward.
Yeah, control and forward key. It should be right next to it. It should be it should be bottom on your right hand side. You're gonna see on top of the question mark and /, they're next to each other.
Okay. And sir, second question is that numerical solution and exact solution. What is the difference between that? Both are calculated one.
Okay, no, the exact solution is not calculated. Exact solution is something you did on a piece of paper, on a pencil. With a piece of paper and pencil, you figure it out. The numerical solution is the one that is computed by your program. This is called numerical solution. So some of you ever took a course in numerical analysis, this actually comes from there. So they use these numerical methods to calculate these numbers. Okay.
Okay, sir.
All right. So, all right. Thank you, everybody. And hopefully see you guys later tomorrow again.
Yeah, hello.
Sir, one more question I have. Like, whatever plot and scatter you have done in Python, so can we do this plot and scatter in C++?
I'm sorry, say again.
Whatever plot and scatter command you have used here, can we do the same thing on C++?
I'm pretty sure you can. I just don't know how, but yes, you can. Short answer is yes, you can. You would have to get some libraries for that. Each one of these has their own library.
Okay, sir. Thank you.
Okay, thank you.
So, thank you, dear participants. So, with this, we come to an end of day 7 of this program. So, dear participants, we, on behalf of the entire team of IIT Academy and Professor Gaurav Trivedi sir, the principal investigator of IIT Academy and the course coordinator from IIT Guwahati, Dr. Aryabharta Sahu sir, I thank you, Ashwini Kumar sir, for coming over this platform and guiding all the participants. So on behalf of Mr. Kaushalendra Singh Sisodia sir also, I thank you sir for accepting our invitation and joining us today. Thank you.
Thank you. So by the way, I'm going to put this file in the WhatsApp group, and this way you can access the file. It's in the WhatsApp group. Okay.
Okay,
Thank you.
so we will be sharing all the details, all the presentation slides and notebooks of today. By the end of the day, recordings will also be shared with you, and the attendance will be updated by the end of the day. Thank you all. Thank you, dear participants. So tomorrow also we will be joining at the same time from 10 onwards using the same link. Thank you all. So participants, you can log out from this link.
What time you will go?
7 o'clock.
Oh,
So
7 o'clock. Yeah.
the meeting
Uh-huh.
link will be
Still
deactivated
time
in
is
another
there.
2 minutes.
No,
Thank you.
did you transfer money to? First, I will talk to him because yesterday I talked. He did not